So, here's something that might settle quietly in your mind as you lie there. Right now, your brain is solving a small, silent equation just to keep your eyes closed. It is balancing the chemicals that make you feel sleepy against the ones that keep you alert, adjusting the mixture second by second, the same way you might adjust one side of a scale until it finally settles level with the other. You do not feel it happening. You are not meant to. But somewhere inside your skull, something is being solved for, patiently, without any effort on your part at all. Tonight we are going to walk through all of algebra, from the very beginning, the very first people who needed it, all the way through to the ideas that quietly run your phone, your bank account, and the traffic lights you drove past earlier today. By the end, you will understand what algebra actually is, underneath all the letters and symbols, and why it was never really about X at all. It was always about balance. It was always about finding what is missing. If you fall asleep somewhere along the way, that is perfectly fine. That is the point, actually. You do not need to remember any of this by morning. The ideas will still be here if you want to come back to them, and even if you do not, something quiet will have settled in anyway, the way a room settles after someone has been speaking gently in it for a while, long after the words themselves have faded. So let us start at the very beginning, long before anyone had a word for algebra at all, in a place with rivers on either side of it, and clay instead of paper. Around 4,000 years ago, in the land between the Tigris and the Euphrates rivers, in what we now call Iraq, there were scribes who spent their days pressing symbols into wet clay with a reed stylus. This was Babylon, and the people there were remarkably practical. They were not interested in beauty for its own sake. They were not philosophers sitting in gardens wondering about the shape of the universe. They were interested in taxes, in land, in grain, in how much silver a debt was worth, and in how to divide an inheritance fairly among several children. These are the kinds of problems that force a civilization to invent mathematics, whether they mean to or not. When you have to figure out how much grain each farmer owes the temple, and the fields are all different sizes, and some years the harvest is better than others, you need a system. You need a way of thinking that can handle unknowns without panicking. The Babylonians left behind thousands of clay tablets, and archaeologists have found many of them buried in the ruins of old cities, some of them so ordinary they were clearly just homework. A teacher would write a problem on one tablet, and a student would work through it on a smaller tablet, the same way a child today might work through a page of arithmetic at the kitchen table. You can almost see the student's hand, pressing a little too hard in places, erasing a mistake with a thumb while the clay was still wet. These were real people, sitting somewhere trying to figure something out, 4,000 years ago. One famous tablet, now called Plimpton 322, sits in a collection at Columbia University, and it contains rows of numbers that mathematicians have spent 100 years arguing over. Most now agree that it lists what we would call Pythagorean triples, sets of three numbers that describe the sides of a right triangle, worked out centuries before Pythagoras existed. The Babylonians were doing serious, structured mathematics almost 2,000 years before ancient Greece produced its famous names. They were not just counting on their fingers. They were exploring patterns, looking for relationships, building a body of knowledge that would echo down through every century since. What the Babylonians did not have was a symbol for an unknown number. When they wanted to solve what we would now write as an equation with an X in it, they wrote the whole problem out in words, in full sentences, the way you might explain a recipe to a friend over the phone. A tablet might say something like, "I have added the length and the width of a rectangle and gotten a certain number, and the area is another certain number. Tell me the length and the width." Then it would walk through the steps to solve it, in prose, carefully, deliberately, no letters, no plus signs, no equals sign. Just patient, repeated language, describing a process. And here is the important part, the part worth sitting with for a moment, before you drift any further. Even without any symbols at all, the Babylonians were doing algebra. Algebra is not really about the symbols. The symbols came much later, and we will get to them in time. Algebra, at its heart, is a method, a way of thinking about an unknown quantity as if it were a known one, giving it a placeholder in your mind, and then working backward through a sequence of allowed moves until the placeholder reveals its true value. The Babylonians had the method. They understood it deeply. They just wrote it out longhand, the way you might write out a full paragraph describing long division, instead of using the little symbol for it. They also had specific techniques that mathematicians recognize today. They knew how to complete the square, a technique we will explain properly a little later tonight, and they used it to solve what we now call quadratic equations, equations where the unknown number is multiplied by itself. They worked these out using areas, actually drawing or imagining squares and rectangles, and adjusting them, the way you might rearrange furniture in a room until it fits properly against the walls. This geometric way of thinking about equations, using shapes to understand relationships between numbers, would matter again much later, when it resurfaced in a different civilization on the other side of the world. Meanwhile, in ancient Egypt, scribes were solving similar problems using a method historians now call the method of false position. If you needed to find an unknown quantity, you would simply guess a convenient number, any number that made the arithmetic easy. Work through the entire problem using that guess, see how far off the final answer was, and then scale your guess up or down proportionally until it landed exactly right. It sounds almost too simple to work, but it works beautifully for a wide range of problems, and versions of this method were still being taught in arithmetic books hundreds of years later, long after more modern algebra had been invented. The Rind Papyrus, an Egyptian document from around 1650 BCE, contains dozens of these problems, worked carefully by hand, the answers checked and rechecked. You can picture a scribe sitting somewhere near the Nile, dipping a reed into ink, working through a problem about dividing loaves of bread among workers, using this method of guessing and adjusting, until the numbers finally lined up. There is something deeply human in that. The willingness to be wrong at first, to make a reasonable guess and then refine it patiently, rather than demanding to be right on the first try. So already, in these two early civilizations, we can see the two ingredients that would eventually combine into algebra as we know it. From Babylon, we get systematic procedures, step-by-step methods that could be taught and repeated, applied to an unknown quantity, treated as if it were known. From Egypt, we get the deep comfort with proportion and adjustment, the idea that you can approach a correct answer through careful, reasoned guessing and refinement, getting closer and closer until you land exactly where you need to be. Neither civilization had the word algebra, neither had our symbols. But both had already discovered something true and lasting. They had discovered that numbers follow rules, and that those rules can be used to find what is hidden. The Babylonians, sitting beside their two rivers, pressing their styluses into clay, understood that an unknown quantity was not a terrifying void. It was just something you had not named yet. You could treat it like any other number, move it around, combine it with things you already knew, and eventually, through enough careful steps, it would have to show itself. The Egyptians, working along their one great river, understood that you did not have to be right on the first attempt. You could start with something close, something reasonable, and let the structure of the problem itself guide you toward the true answer, correcting your initial guess as you went. These are not separate ideas, really. They are two faces of the same deep insight, the insight that an unknown is not permanently unknowable. It is just temporarily hidden, and there are reliable, repeatable ways to bring it into the light. This insight would travel, slowly, over centuries, carried by traders and translators and scholars, passed from one civilization to the next, sometimes written down, sometimes spoken, sometimes nearly lost and then found again. It would take many more centuries, and the mathematics of several more civilizations, layered one on top of another, before anyone would give this way of thinking a name. The name, when it finally arrived, would come from a book written far from Babylon and far from Egypt, in a city that had become one of the great centers of learning in the entire world. Let us move there now, gently, the way a river moves, carrying an idea slowly downstream through centuries, without hurry, without forcing anything. By around the year 820, the city of Baghdad had become one of the intellectual centers of the world. The Caliph at the time had established something called the House of Wisdom, a combination of library, translation center, and research academy, where scholars gathered texts from Greece, from Persia, from India, and from Babylon's own mathematical tradition, and worked to translate them, understand them, and build on them. Imagine a great building filled with scholars speaking different languages, comparing manuscripts, arguing gently about the best way to render a particular Greek word into Arabic, copying out diagrams by lamplight. It was in this environment, surrounded by centuries of accumulated mathematical knowledge from many different cultures, that a scholar named Muhammad ibn Musa al-Khwarizmi wrote a book that would change the course of mathematics. The book's full title translates roughly as The Compendious Book on Calculation by Completion and Balancing. In Arabic, the word for completion is al-Jabr. That word, al-Jabr, traveled with the book as it was translated into Latin centuries later, and it slowly transformed, through the mouths of scholars in different languages, across different centuries, into the word we use today, algebra. What did al-Jabr actually mean? It referred to a specific operation, the operation of restoring balance to an equation by moving a quantity from one side to the other. Imagine you have a simple balance scale, the old-fashioned kind, with two pans hanging from a bar. If you have 5 apples on one side, and you know they balance against 3 apples and something else on the other side, you can remove 3 apples from both sides and the scale will still balance, perfectly level, undisturbed. That act of removing the same thing from both sides to simplify the picture, that is what al-Jabr described. It is the exact same operation you learned, or will learn, or perhaps already sort of remember, when you move a number from one side of an equation to the other and it flips its sign in the process. That flip is not a magic trick. It is not an arbitrary rule someone invented to make school more difficult. It is just the visible trace of something being removed equally from both sides of a balance, so that the scale stays level while the picture gets simpler. Al-Khwarizmi's book worked through 6 standard types of equations, all involving what we would now call squares of unknowns, unknowns themselves, and plain numbers, and it showed methodically how to solve every single one of them using a small toolkit of moves. He included this idea of al-Jabr, restoring balance, and a second idea called al-Muqabala, which meant balancing or comparing, essentially combining like terms on each side before you start moving anything across. Sound familiar? It should. This is the exact same 2-step dance you use today when you solve an equation. First, you simplify each side by combining anything that matches. Then, you move terms across the equals sign, flipping their sign as they cross, until the unknown sits alone on one side, fully revealed. Al-Khwarizmi did all of this without our modern symbols too. He wrote his equations out in words, much like the Babylonians had, but his method was far more general, far more systematic. He was not solving one specific problem about a particular rectangle's area. He was laying out, once and for all, the complete menu of equation types you could ever encounter, at least at that level of complexity, and providing a guaranteed method for solving each one. He also included geometric proofs, borrowed and refined from that older Babylonian tradition of thinking about equations, using squares and rectangles, showing why each method actually worked, and not just that it worked. This is worth pausing on for a moment because it points to something important about what algebra really is, underneath everything. Algebra is not primarily about finding one answer to one problem. Arithmetic does that. Algebra is about finding a method that works for an entire category of problems at once. When you learn how to solve one quadratic equation using the quadratic formula, you have not just solved that one equation, you have solved every quadratic equation that will ever exist, because the method generalizes completely. That leap, from solving individual problems to solving entire families of problems using one reusable method, is the leap that al-Khwarizmi made explicit and systematic in a way no one quite had before him. His name itself, al-Khwarizmi, eventually gave us another word entirely. Through a slightly different chain of translation and mispronunciation across centuries and languages, it became the word algorithm, which now describes any step-by-step procedure for solving a problem, whether that problem involves numbers, a recipe, or the code running inside your phone right now, deciding which video to show you next. So this one person in 9th century Baghdad gave the world two words that now sit at the very center of mathematics and computer science both. Algebra, the method of balancing an unknown against the known, and algorithm, the very idea of a repeatable, reliable procedure. His work did not stay in Baghdad. It traveled, the way ideas do, carried by scholars and translators across borders and centuries, slowly reshaping how people thought about numbers, about unknowns, about the patient art of finding what is missing. Now let your eyes stay closed if they are already closed. Let your breathing stay slow and even. The story will continue on its own, and you do not need to hold on to any of it. The scale is already level. The balancing is already happening, without your help, the way it always has. Let's move there now, gently, the way a river moves, carrying an idea slowly downstream through centuries, without hurry, without forcing anything. By around the year 820, the city of Baghdad had become one of the intellectual centers of the world. The caliph at the time, a man named al-Ma'mun, had established something called the House of Wisdom, a combination of library, translation center, and research academy, where scholars gathered texts from Greece, from Persia, from India, and from Babylon's own mathematical tradition, and worked to translate them, understand them, and build on them. Imagine a great building filled with scholars speaking different languages, comparing manuscripts, arguing gently about the best way to render a particular Greek word into Arabic, copying out diagrams by lamplight long into the night. The air would have smelled of ink and papyrus, and the faint dust of old scrolls being unrolled carefully by hands that understood exactly how precious they were. It was in this environment, surrounded by centuries of accumulated mathematical knowledge from many different cultures, that a scholar named Muhammad ibn Musa al-Khwarizmi wrote a book that would change the course of mathematics. Al-Khwarizmi was a Persian mathematician who worked at the House of Wisdom, and he had access to texts that most scholars of his era could only dream of seeing. Greek geometry, Indian arithmetic, Babylonian calculation methods, all of it sat before him, waiting to be synthesized. What he did with that material was not simply translate it, he wove it together into something new, something more general and more systematic than anything that had come before. The book's full title translates roughly as The Compendious Book on Calculation by Completion and Balancing. In Arabic, the word for completion is algebra. That word, algebra, traveled with the book as it was translated into Latin centuries later, and it slowly transformed, through the mouths of scholars in different languages, across different centuries, into the word we use today, algebra, a single word, carrying inside it the memory of a 9th century book, written in a city built beside the Tigris River, by a man who was trying to make the solving of problems into something systematic and teachable, rather than something mysterious and scattered. What did algebra actually mean? It referred to a specific operation, the operation of restoring balance to an equation by moving a quantity from one side to the other. Imagine you have a simple balance scale, the old-fashioned kind with two pans hanging from a bar. If you have 5 apples on one side, and you know they balance against 3 apples and something else on the other side, you can remove 3 apples from both sides, and the scale will still balance, perfectly level, undisturbed. That act of removing the same thing from both sides to simplify the picture, that is what algebra described. It is the exact same operation you learned, or will learn, or perhaps already sort of remember, when you move a number from one side of an equation to the other, and it flips its sign in the process. That flip is not a magic trick. It is not an arbitrary rule someone invented to make school more difficult. It is just the visible trace of something being removed equally from both sides of a balance, so that the scale stays level while the picture gets simpler. If you have x plus 3 equals 10, and you subtract 3 from both sides, the plus 3 on the left becomes 0, and the 10 on the right becomes 7. The plus 3 did not magically become a minus 3 as it jumped across the equals sign. It was simply removed, equally, from both sides at once. The minus 3 you see on the right is just the record of that removal, the footprint left behind after the operation was complete. Al-Khwarizmi's book worked through 6 standard types of equations, all involving what we would now call squares of unknowns, unknowns themselves, and plain numbers. He classified every possible equation of this kind into one of these 6 types, and then he showed methodically how to solve every single one of them using a small toolkit of moves. His toolkit included this idea of algebra, restoring balance by moving terms from one side to the other, and a second idea called al-Muqabala, which meant balancing or comparing, essentially combining like terms on each side before you start moving anything across. If you had an equation with several terms involving the unknown on one side and several on the other, you would first use al-Muqabala to tidy up each side individually, combining everything that matched into a single, cleaner expression. Only then, once each side was as simple as possible, would you use algebra to move terms across the equals sign, restoring balance step by step until the unknown sat alone on one side, fully revealed. Does this sound familiar? It should. This is the exact same 2-step dance you use today when you solve an equation. First, you simplify each side by combining anything that matches. Then, you move terms across the equals sign, flipping their sign as they cross, until the unknown sits alone. The words have changed over the centuries. The notation has been streamlined almost beyond recognition, but the underlying moves, the actual logical steps you perform, are identical to what al-Khwarizmi wrote down in Baghdad more than 1200 years ago. Al-Khwarizmi did all of this without our modern symbols too. He wrote his equations out in words, much like the Babylonians had, but his method was far more general, far more systematic. He was not solving one specific problem about a particular rectangle's area. He was laying out, once and for all, the complete menu of equation types you could ever encounter, at least at that level of complexity, and providing a guaranteed method for solving each one. He also included geometric proofs, borrowed and refined from that older Babylonian tradition of thinking about equations using squares and rectangles, showing why each method actually worked, and not just that it worked. This is worth pausing on for a moment, because it points to something important about what algebra really is, underneath everything. Algebra is not primarily about finding one answer to one problem. Arithmetic does that. If you need to know what 7 times 8 is, arithmetic gives you 56, and that is the end of it. Algebra is about finding a method that works for an entire category of problems at once. When you learn how to solve one quadratic equation using the quadratic formula, you have not just solved that one equation. You have solved every quadratic equation that will ever exist, because the method generalizes completely, without exception, forever. That leap, from solving individual problems to solving entire families of problems using one reusable method, is the leap that al-Khwarizmi made explicit and systematic in a way no one quite had before him. The Babylonians had solved individual quadratic problems. The Egyptians had solved individual proportion problems. But al-Khwarizmi wrote the manual. He laid out the full classification, the complete set of types, and the guaranteed method for each one. Once you had read his book and understood it, you could solve any problem of that class, no matter what numbers appeared in it, no matter whether you had ever seen that particular problem before. His name itself, al-Khwarizmi, eventually gave us another word entirely. Through a slightly different chain of translation and mispronunciation across centuries and languages, it became the word algorithm. In Latin translations of his work, his name was often rendered as algoritmi, and over time, that word detached from the man himself and became the general term for any step-by-step procedure for solving a problem. An algorithm is simply a set of instructions laid out in order that, if followed exactly, will reliably produce a correct result. A recipe is an algorithm. The directions your phone gives you when you ask for the fastest route are an algorithm. The code running inside that same phone right now, deciding which video to show you next, is an algorithm. Every one of those algorithms traces its name, etymologically, back to one Persian mathematician working in 9th century Baghdad, trying to make problem-solving into something systematic and teachable. So this one person gave the world two words that now sit at the very center of mathematics and computer science both. Algebra, the method of balancing an unknown against the known, and algorithm, the very idea of a repeatable, reliable procedure. It is difficult to think of many other individuals in history who have left their names so thoroughly woven into the fabric of how we think about thinking itself. Al-Khwarizmi's work did not stay in Baghdad. It traveled, the way ideas do, carried by scholars and translators across borders and centuries. Islamic scholars across the following centuries, in cities like Cairo, Cordoba, and Damascus, continued refining these ideas, extending them to more complicated equations, and connecting algebra more deeply with geometry. They did not treat his book as the final word. They treated it as a foundation, something solid to build on. One mathematician in particular, a man named Omar Khayyam, better known in the West for his poetry, spent part of his life working on how to solve cubic equations involving an unknown multiplied by itself 3 times over. Al-Khwarizmi's methods had handled squared unknowns beautifully, but cubed unknowns were a different order of difficulty altogether. Khayyam approached them using intersections of curves, drawing one curve described by one equation and another curve described by another equation, and finding the exact point where they crossed. It was a beautifully visual approach that blended algebra and geometry into a single picture, treating an equation not just as a string of words or symbols to be manipulated, but as a shape that could be seen and studied. This tradition of thinking about equations both symbolically and geometrically as two views of the same underlying truth would prove to be one of the most powerful ideas in the entire history of mathematics. We will return to it again a little later tonight when we talk about graphs and about what it actually means to see an equation rather than just solve it. For now, though, the story moves west, across the Mediterranean, into medieval and then Renaissance Europe, where al-Khwarizmi's book, translated into Latin, would slowly reshape how an entire continent thought about numbers. The problem al-Khwarizmi's ideas faced in Europe was not that people did not want them. It was that European mathematics at the time had almost no efficient system of writing numbers at all. Europe was still largely using Roman numerals, which are wonderful for carving into stone monuments and nearly unusable for actual calculation. Try multiplying the Roman numeral for 47, XLVI, by the Roman numeral for 83, LXXXII, in your head, writing only Roman numerals on paper as you go, and you will quickly understand why European merchants and scholars were desperate for something better. Roman numerals were designed for recording quantities, not for manipulating them. They were a notation for results, not a tool for calculation. That something better arrived gradually, through trade routes and translated texts, in the form of what we now call Hindu-Arabic numerals, the 10-digit system, 0 through 9, that had been developed in India centuries earlier and refined by Arabic mathematicians before making its way into Europe. This system was not just a different set of symbols. It was a fundamentally different way of thinking about numbers, one that used position to convey value, so that the same digit, a 5 say, could mean 5 or 50 or 500, depending on where it sat in the number. And crucially, it included 0, a symbol for nothing, which seems obvious to us now, but was a genuine conceptual breakthrough at the time. An Italian mathematician named Leonardo of Pisa, much better known by his nickname Fibonacci, wrote a hugely influential book in the year 1202 called Liber Abaci, the Book of Calculation, which introduced this number system to European merchants and scholars in a practical, accessible way. Fibonacci did not invent the system. He had learned it from Arab traders during his travels in North Africa and the Mediterranean, and he recognized immediately how much more powerful it was than anything available in Europe at the time. His book was full of worked examples about currency conversion, profit sharing, the calculation of interest, and yes, that famous problem about rabbits that gave us the Fibonacci sequence. Though that sequence is really a small side note in a much larger and more practical book. A curiosity included alongside hundreds of other problems about the daily concerns of merchants and bankers. Once Europe had efficient numerals, algebra could finally take root and grow properly. But it still needed one more thing before it could become the algebra you might remember from school, the tidy arrangement of letters and numbers and symbols that sits on a page looking almost like a sentence written in a foreign language. It needed symbols. For centuries after al-Khwarizmi, mathematicians across multiple cultures continued to write their equations out mostly in words, a style historians now call rhetorical algebra. Even when some abbreviations crept in here and there, a full equation still read more like a paragraph than like the tidy string of symbols you would recognize today. This was slow to write, slow to read, and made it genuinely difficult to see the underlying structure of a problem at a glance. Imagine trying to do algebra homework, where every single step had to be written as a complete grammatical sentence, with subjects and verbs and objects, and you will understand why progress was sometimes slow. The shift towards symbols happened gradually, piece by piece, over roughly 3 centuries, through many different mathematicians in many different countries, each contributing a small piece of notation that eventually stuck and became part of the shared language. A German mathematician introduced the plus and minus signs in the late 1400s, originally as warehouse marks to indicate whether a crate was over or under its expected weight, before mathematicians borrowed them for arithmetic. An English mathematician named Robert Recorde, writing in 1557, grew tired of writing out the words "is equal to" over and over again in his book, and invented the equals sign, 2 parallel horizontal lines, because, in his own words, no 2 things could be more equal than 2 parallel lines of the same length. That is a remarkably tender piece of reasoning to have survived for almost 500 years, still sitting quietly at the center of every equation you have ever seen. The person who arguably did the most to turn algebra into the symbolic language we would recognize today was a French mathematician named François Viète, working in the late 1500s. Before Viète, even when an equation used some symbols, the actual known numbers in the problem were usually still just written as numbers, and it was really only the unknown that got any special treatment, if it got any at all. Viète had the idea of using letters for known quantities too, typically consonants for known numbers, and vowels for unknowns. This meant that for the first time, an equation could be written in a fully general form, describing an entire pattern rather than one specific numerical problem. You could write something like a squared plus b times a plus c equals 0, and that single line of symbols would describe every quadratic equation that could ever exist, no matter what specific numbers a, b, and c happened to stand for. This was the moment algebra truly became abstract in the modern sense, able to describe relationships between quantities in general, rather than just solving one arithmetic puzzle at a time. Viète's notation was still a little awkward by modern standards, using different letters for different roles in a way that has not fully survived. But the essential breakthrough, using letters to stand for any quantity at all, known or unknown, was his. A little later, in the early 1600s, a French philosopher and mathematician named René Descartes refined the notation even further, settling on the convention that is still used today, almost without change. Letters near the end of the alphabet, X, Y, and Z, for unknowns. Letters near the beginning, A, B, and C, for known constants. Small numbers written slightly above and to the right, to show a quantity multiplied by itself a certain number of times, what we now call an exponent. Descartes also did something else, something that would connect algebra to an entirely different branch of mathematics, in a way that changed both fields forever. We will spend real time on that connection a little later tonight, because it is genuinely one of the most elegant ideas in the whole history of thought. For now, just hold on to this. By the time Descartes was finished, algebra finally looked, on paper, like the algebra you have seen in your life. Letters, numbers, small exponents, plus and minus signs, an equals sign made of two parallel lines, a 4,000-year journey from clay tablets in Babylon to a page that would be instantly recognizable to a modern student, arriving at last in the form we still use tonight. Every symbol on that page has a history. Every piece of notation was invented by someone, somewhere, often for reasons that had nothing to do with mathematics at all, and then borrowed and adapted and slowly worn smooth by centuries of use, until it feels as natural and inevitable as the alphabet itself. But notation alone is not understanding. The symbols are just the surface. Now that they existed, mathematicians could ask a much deeper question, one that had been quietly waiting underneath all of this the entire time. What problem was all of this actually trying to solve? What was the real, underlying need that pushed 4,000 years of civilizations, from Babylonian scribes to Renaissance philosophers, to keep refining this one idea, generation after generation, until it became a complete written language of its own? The honest answer is that human beings kept running into situations where they knew something about a quantity, but not the quantity itself, and they needed a reliable way to work backward from what they knew to what they did not. This happens constantly, in ordinary life, far more often than you might expect. A farmer knows the total harvest and the price per basket, and needs to know how many baskets there were. A builder knows the total amount of stone available and the size of each block, and needs to know how many blocks can be made. A merchant knows two people split a profit unevenly, with one getting a certain amount more than the other, and needs to know each person's exact share. In every single one of these situations, there is a hidden quantity, sitting behind a known relationship, and the entire challenge is figuring out how to pull it out into the open, to make the hidden visible. Before algebra had a general method, each of these problems had to be solved somewhat individually, often through trial and error, or through specialized tricks that worked for one narrow situation and nothing else. This is actually a perfectly reasonable way to survive as a species for quite a long time. Most problems people faced day to day were simple enough that guessing and checking, or applying a known trick, worked well enough to get by. But as societies grew larger, as trade routes stretched further, as buildings grew taller and more ambitious, as astronomers tried to predict the motion of planets years in advance, the problems people needed to solve grew more complicated. They involved more unknowns tangled together at once, more relationships layered on top of each other, and guessing simply stopped being good enough. The old tricks broke down under the weight of complexity. What people needed was not a bigger bag of individual tricks. They needed a single, general method, one that would work no matter what specific numbers were involved, one that could be taught to a student who had never seen that particular problem before and still let them arrive confidently at the correct answer. That is the deep, underlying need that algebra answers. It replaces 1,000 individual tricks with one small set of universal moves, moves that work every single time, on every single problem of that shape, regardless of the specific numbers plugged in. The method does not care whether the unknown is a number of baskets, a number of blocks, or a number of coins. The method only cares about the structure of the relationship, the shape of the balance between what is known and what is hidden. And that structure, that shape, is the same across an enormous range of human concerns. The same algebra that helps a merchant divide a profit fairly also helps an engineer calculate the load on a beam, also helps an astronomer predict the return of a comet, also helps a doctor determine the right dosage of a medicine. The problems look different on the surface, but underneath they share the same bones, the same quiet architecture of known and unknown, balanced against each other, waiting to be untangled. The scale is still level, the river is still moving. The words of al-Khwarizmi, written by lamplight in a city beside the Tigris, are still echoing, quietly, in every equation solved tonight, whether by a student at a desk or by a processor inside a phone, running through the same steps he laid out 12 centuries ago, just much, much faster now, too fast for any human eye to follow. Let's actually build this idea now, slowly, the way you might build something with your hands in low light, feeling each piece before setting the next one down. Imagine, for a moment, an actual balance scale, the old kind, two pans hanging from a horizontal bar, resting on a central point. If the scale is level, both pans hold exactly the same weight. This is not a metaphor for an equation. This is, quite literally, what an equation is. The equal sign is a picture of perfect balance between two pans. When Robert Recorde drew those two parallel lines in 1557, he was not inventing a new concept. He was drawing a picture of something ancient and intuitive, something every child understands the first time they sit on a seesaw and feel it tip one way, then the other, then settle perfectly still in the middle. Now suppose you know that one pan holds a small bag of an unknown weight, plus 3 separate 1-pound weights, and the other pan holds exactly 10 pounds, and the whole thing is perfectly level. You do not know what is in the bag, but you know the scale balances. What can you do? You can think about it for a moment. You can notice that if the bag were not there, the 3 pounds on the left would not balance against 10 pounds on the right. So the bag must be making up the difference. But how much exactly? You could remove 1 pound from each side. The scale stays level, because you took the same amount away from both pans equally. This is the key move, the only move that really matters. Whatever you do to one side, you must do exactly the same thing to the other side, and the balance will hold. Now one side holds the bag plus 2 pounds, and the other side holds 9 pounds. Remove another pound from each side. Now the bag plus 1 pound balances against 8 pounds. Remove 1 more pound from each side. Now the bag alone balances against 7 pounds. And there it is. Without ever opening the bag, without ever weighing it directly, without guessing or hoping or approximating, you now know, with complete certainty, that the bag weighs exactly 7 pounds. You did not need to see inside it. You did not need a bigger scale or a more precise instrument. You simply made a series of small, careful, equal adjustments to both sides of a balanced situation, until the unknown quantity was left standing alone, fully revealed, with nothing else beside it. That is algebra. That is the whole idea, in its purest and simplest form. You never had to guess. You never had to open the bag. You reasoned your way to the answer by making a series of fair moves, moves that never disturbed the balance, only simplified it, step by careful step. Each move was small enough that you could be completely sure it was correct, and when you were finished, the unknown had no choice but to show itself, because everything else had been carefully, patiently removed. Now here is where the letters come in, and I want you to notice that the letter itself is doing almost nothing magical. The letter X is simply a shorter, tidier way of saying the bag, or the unknown weight, or the number I do not know yet. If we write the bag's weight as X, then the situation on the scale becomes X plus 3 equals 10. That is it. That is the entire equation. It says, in the shortest possible way, that some unknown amount plus 3 balances against 10. The X is not mysterious. It is not a code to be cracked. It is just a name, a placeholder, a blank line on a form waiting to be filled in. And solving the equation means doing exactly what you did with the actual weights, just written down instead of physically lifted off a scale. You remove 3 from both sides. On the left, X plus 3 minus 3 leaves just X. The plus 3 and the minus 3 cancel each other out perfectly, leaving the unknown standing alone. On the right, 10 minus 3 leaves 7, so X equals 7. The letter X was never hiding anything from you. It was simply standing in for a number whose identity you did not yet know, waiting patiently while you worked out, through balanced, careful steps, exactly what it had to be. This single insight that you can treat an unknown as if it were a known quantity, give it a name, and manipulate it using consistent rules until its true value is revealed, is really the entire foundation of algebra. Everything else that follows tonight, every technique, every branch, every application, is really just this same idea, applied to more complicated situations, with more unknowns, more layers, and more elaborate relationships tangled together. But underneath all of that complexity, it is always this same balance scale. It is always this same quiet process of removing equal amounts from both sides until only the unknown remains, standing alone, finally visible. The unknown does not fight back. The unknown does not resist. It simply waits. And if you are patient enough, if you make only fair moves that respect the balance, the unknown will eventually have to reveal itself. There is something almost gentle about that, something reassuring. The problem is not hostile. It is just waiting to be understood. There is one more piece worth adding here, before we move into the first real breakthrough in the history of algebra, because it will matter enormously later. Not every unknown appears just once, added or subtracted plainly. Sometimes an unknown is multiplied by itself, the way you might stack a square shape on top of itself to find its area. If you have a square room and you know one side of it, the area is that side length multiplied by itself. If the side is 5 feet, the area is 25 square feet. The side length appears twice in that calculation, multiplied together. When a quantity is multiplied by itself, mathematicians write a small 2 just above and to the right of the letter, and this is called squaring the quantity, or raising it to the second power. An unknown multiplied by itself twice more, 3 times in total, is called cubing it, or raising it to the third power, and you can imagine this as the volume of a cube rather than the area of a square. If you have a cube-shaped box, and you know the length of one edge, the volume is that edge length multiplied by itself 3 times. These small numbers sitting up in the corner, called exponents, tell you how many times a quantity has been multiplied by itself, and equations that include a squared unknown, rather than just a plain one, behave quite differently. They are not as simple as removing the same amount from both sides until the unknown stands alone. The unknown is tangled up with itself, multiplied by itself, and ordinary addition and subtraction cannot untangle it directly. This is the kind of equation that requires a cleverer set of tools to solve. And that cleverness is exactly what the first great breakthrough in algebra provided. It happened remarkably early, well before al-Khwarizmi, well before Descartes, in that same ancient world we began with tonight. The Babylonians, sitting beside their 2 rivers, pressing their styluses into wet clay, worked out how to solve these squared equations by thinking about them not as strings of symbols, but as shapes. They thought about squares and rectangles, about areas and sides, and they found a way to rearrange the pieces until the unknown revealed itself. So let us talk properly now about completing the square, the technique the Babylonians worked out, that al-Khwarizmi later formalized and proved geometrically, and that still sits underneath one of the most useful formulas in all of algebra today. This is not a detour into something complicated. This is the heart of the matter, and it is much simpler than it sounds. Imagine you have a square garden bed, and you do not know its side length yet. You only know something about its area, combined with some extra strips of land added onto it. Say, for instance, that a square garden bed, plus 2 strips of land, each as long as one side of the square and 4 feet wide, together cover an area of 45 square feet. You want to know how long one side of the original square garden bed actually is. Just the square part, not the strips. If you tried to solve this using only plain arithmetic, you would be stuck. The unknown length is multiplied by itself in the square part, but only added once in each strip. These 2 behaviors do not mix easily using ordinary addition and subtraction. You cannot simply subtract the strips away, because they are attached to the square, and their length depends on the very side length you are trying to find. This is exactly the kind of problem that stumped mathematicians until someone had a wonderfully physical idea. What if, instead of fighting with the shape as it is, you rearranged it, physically, into a shape that actually is a perfect square, with no strips attached, no awkward protrusions, and then measured that new perfect square instead? If you can turn the whole messy shape into one clean square, you can find its side length easily, because a square's side is just the number that, multiplied by itself, gives the area. Here is how it works. Take those two strips, each 4 feet wide, and instead of attaching them both to 2 full sides of the square, split each one in half. So you now have 4 thin strips, each 2 feet wide, and attach one to each of the 4 sides of the square evenly, like a picture frame going around it. This uses exactly the same total area as before. Nothing added, nothing removed, just rearranged, the way you might rearrange furniture in a room without buying anything new. Now look at what you have. A square in the middle, with 4 thin strips around its edges, but the 4 corners of this frame are still empty. There are missing little 2-foot by 2-foot squares in each corner. The shape is almost a perfect square, but not quite. It has those 4 empty corners. If you fill in those 4 small corner squares, each with an area of 4 square feet, 16 square feet total, you now have one single, larger, perfect square, with no gaps, no missing corners, a clean shape from edge to edge. You have added 16 square feet of area, but you know exactly how much you added and where you put it. And here is the beautiful part. You know the area of everything except those 4 corner pieces, because that was the 45 square feet you started with. The original garden bed and its strips covered 45 square feet. So the area of this new, larger, complete square is 45 plus 16, which is 61. And because it is a perfect square, you can find its side length simply by asking, what number, multiplied by itself, gives 61? That number is the side length of your larger square, the one with the frame all filled in and complete. Once you have that larger side length, you subtract the 2 feet of frame you added to each side, the width of the strips you attached, and you have the length of your original, unknown garden bed, revealed at last, without ever needing to measure it directly. The unknown has been found, not by guessing, not by a lucky insight, but by a careful, physical rearrangement that anyone could do with a piece of paper and a pencil, or even just by imagining it clearly. This is completing the square. You take an imperfect, awkward shape, and you deliberately add a carefully chosen extra piece to it, transforming it into a perfect, clean square, something you already know how to measure. Then you simply subtract that extra piece back out at the end, once you have your answer. You borrowed a small amount of area temporarily, used it to tidy the shape into something recognizable, and then gave it back. It is, in a very real sense, the algebraic version of tidying up a messy room by temporarily adding a few organizing boxes, sorting everything into a clean arrangement, and then removing the boxes once you understand exactly what you have and where everything belongs. Modern algebra performs this exact same trick using symbols instead of a physical garden bed, and it works on any equation where an unknown is squared. You take the plain, non-squared part of the equation, divide it by 2, square that result, and add it to both sides. Doing this always transforms the awkward left side into something that can be written as a perfect square, a single quantity multiplied by itself. From there, solving is simple. You find what number, multiplied by itself, gives you the right side, and then you undo the small adjustment you made earlier to isolate the unknown completely. It is precisely the same reasoning as the garden bed frame, just performed with letters and numbers instead of soil and stone. This technique matters enormously because centuries later, mathematicians realized that if you perform completing the square in the most general way possible, using letters to stand for any numbers at all, rather than one specific numerical problem, you can derive a single formula that solves every possible equation of this squared type, forever, without ever having to complete the square by hand again. That formula, often just called the quadratic formula, is really nothing more than completing the square, done once, generally, and then written down so nobody has to redo that careful geometric rearranging every single time they encounter a new squared equation. The quadratic formula looks intimidating, written out with a square root symbol and several letters. Many people remember it from school as something to memorize, something that appeared on tests and then was promptly forgotten. But every single piece of it is simply a frozen record of the steps we just walked through together. The strips, the frame, the missing corners, filled in and then subtracted back out. The square root symbol is there because at the end you need to find what number multiplied by itself gives a certain result. The letters A, B, and C are just placeholders for whatever numbers happen to appear in a particular equation. The whole thing is a machine, a very compact machine, that does the completing of the square automatically. I want to say this plainly, because it is easy to forget once a formula gets memorized. The quadratic formula is not a separate, mysterious piece of mathematics that somebody simply invented out of nowhere. It is a shortcut. It is a compressed version of an ancient, physical, geometric idea about rearranging garden beds into perfect squares. Every time it is used, whether by a student, an engineer, or a piece of software silently running inside a bridge design program, it is quietly performing that same act of tidying an awkward shape into a clean one, just far too quickly for anyone to notice the tidying happening at all. Think about that for a moment. Every bridge you have ever crossed, every building you have ever walked through, every arch that has curved gracefully over your head, was likely designed with the help of this formula, and this formula itself is just the recorded memory of a Babylonian scribe, 4,000 years ago, imagining a garden bed with strips attached, and figuring out how to rearrange it into a clean square. The continuity of that thought, across all those centuries, across all those civilizations, is something worth sitting with quietly. Now, this first great breakthrough, completing the square, handled equations where an unknown was squared, multiplied by itself once. But mathematicians in later centuries kept encountering situations where an unknown needed to be cubed, multiplied by itself twice over, or raised to even higher powers still. A cubed unknown might describe the volume of a container. A fourth power unknown might describe something even more elaborate. And this development, this steady climb toward more complicated equations, involving more unknowns tangled together and higher powers layered on top of each other, is really the story of how algebra grew from a useful set of tricks into the vast, structured field it is today. Italian mathematicians in the 1500s, working in an intensely competitive culture of public mathematical contests, where rival scholars would challenge each other to solve difficult problems in front of an audience, worked out general methods for solving cubic equations, and shortly after, equations involving a fourth power as well. These methods were considerably more elaborate than completing the square. They involved clever substitutions, swapping one variable for another, in a way that transformed a messy equation into a different, more manageable one, solving that simpler version and then translating the answer back into the original variable. It is worth knowing that this era produced real personal drama around mathematics. Scholars guarded their solution methods as closely as trade secrets, sometimes for years, before eventually publishing them or having them extracted through public challenge matches. Mathematics, at this point in history, was not always the calm, cooperative pursuit it can feel like today. It was, at times, a genuine competitive sport, with reputations and livelihoods on the line, with whispered accusations and dramatic public reveals. Alongside these more advanced techniques, another development was quietly reshaping algebra just as profoundly, and this one had nothing to do with new formulas at all. It was the slow, hard-won acceptance of negative numbers and of zero as legitimate numbers in their own right, worthy of full citizenship inside an equation. This might sound strange to hear, because negative numbers probably feel completely ordinary to you. You see them on weather reports, on bank statements, on thermometers. But for a very long time, many mathematicians, even brilliant ones, were deeply uncomfortable with the idea of a number less than nothing. How can you have -3 apples? What would that even look like, sitting on a table in front of you? It seemed like nonsense, like a word that referred to nothing real. Early algebra, including much of al-Khwarizmi's work, often avoided negative numbers entirely by very carefully sorting equations into separate categories, depending on which terms were positive. If an equation had a negative term, it was moved to the other side and treated as a different type of problem altogether. They worked around the discomfort rather than confronting it directly. It took mathematicians in India, working somewhat earlier and largely independently of the European tradition, to fully embrace negative numbers as genuine, usable quantities. They understood them not as some kind of impossible nonsense, but as representing debt or direction or a deficit, something perfectly sensible once you stopped insisting that every number had to represent a pile of physical objects you could hold in your hand. A debt of 3 coins is as real as a profit of 3 coins. It just points in the opposite direction. A mathematician named Brahmagupta, writing in the 7th century, laid out clear rules for how negative numbers behave, in addition, subtraction, multiplication, and even worked out rules for zero. He understood that any number multiplied by 0 gives 0, a fact that seems obvious now, but had to be stated explicitly at the time. He also grappled with the far trickier question of what happens when you try to divide by 0. A question so strange that mathematicians still handle it carefully today, essentially declaring the operation undefined rather than pretending it has a normal answer. This acceptance of negative numbers changed algebra enormously, because it meant an equation no longer needed to be split into several separate cases depending on the signs involved. One single unified method could now handle every situation, positive, negative, and 0 alike, without special exceptions carved out for each case. This might sound like a small bureaucratic convenience, but it was actually a profound conceptual leap, roughly as significant as the leap from writing equations out in full sentences to writing them with symbols. It meant algebra could finally become truly general, truly universal, applying the exact same rules everywhere, without needing to check first whether a number happened to be friendly or awkward. The balance scale still works with negative numbers. You can think of a negative weight as a small helium balloon tied to the pan, pulling upward instead of pressing downward. The rules are the same. Whatever you add or remove from one side, you add or remove from the other. The balance holds. The method does not change. The unknown still waits, patiently, to be revealed. With negative numbers accepted, with symbolic notation established, and with methods for solving equations up through the 4th power worked out, algebra by the 1600s and 1700s had grown from a set of practical tricks into something closer to a genuine, coherent language, capable of describing an enormous range of situations using the same small toolkit of moves, again and again. And it was around this same time that algebra formed one of the most important partnerships in the entire history of mathematics, joining forces with an entirely different way of thinking about the world, one built not on symbols and equations, but on shapes, positions, and pictures. If you are still with me, let your eyes close now if they are not already. You do not need to follow every word from here. Just let it wash over you, slow and even, like water finding its way around stones in a shallow stream. The explanation continues either way, and there is nowhere you need to keep up with it. The scale is level, the balance is holding, and somewhere in the quiet, the unknown is waiting, patiently, to be understood. René Descartes, the same mathematician who helped settle our modern notation, had another idea, one that quietly changed mathematics forever. It came to him, according to a story that may or may not be entirely true, while he lay in bed one morning, watching a fly crawl across the ceiling near the corner of his room. He realized that he could describe the fly's exact position at any moment using just 2 numbers, how far it was from one wall and how far it was from the other. 2 numbers, and only 2 numbers, could pin down any point on that flat ceiling with complete precision. Wherever the fly moved, its location could be captured, exactly, by those 2 measurements. This became the coordinate system, sometimes called the Cartesian plane, after Descartes' own name. Picture 2 number lines, crossing each other at a right angle, like a plus sign stretched out flat. One line runs left and right, the other runs up and down. The crossing point, where both lines meet, is marked 0 on each. Any point on this flat surface can now be described using exactly 2 numbers, how far right or left of the crossing point it sits, and how far up or down. A point that sits 3 steps to the right and 2 steps up is recorded as 3 and 2. A point 4 steps left and 1 step down is recorded as -4 and -1. Every single point on that entire infinite flat surface now has a name, a pair of numbers that belongs only to it. And here is the beautiful, connective idea, the one worth settling into slowly. If you have an equation involving two unknowns, say x and y, you can find every single pair of numbers that makes that equation true, and mark each pair as a point on this flat surface. When you do this for every possible true pair, all those points together form a shape, a curve, a line, something you can actually see with your eyes. The equation stops being a string of symbols to be solved and becomes a picture, something visual, something you can look at and understand in a different part of your mind. This meant that algebra and geometry, which had developed somewhat separately for thousands of years, each with their own tools and traditions, were suddenly revealed to be two views of the exact same underlying truth. Geometry had always been about shapes, about lines and circles and curves, about things you could draw with a compass and a straight edge. Algebra had always been about equations, about balancing unknowns against knowns, about finding what was hidden. Descartes showed that these were not two separate subjects at all. An equation was a shape was an equation. They were the same thing, seen from two different angles. An equation was not just a string of symbols to be solved, it was also, simultaneously, a picture, a shape, a curve drawn across a flat surface. Solving an equation with one unknown became the same thing as finding where a curve crosses a particular line, usually the flat horizontal line that runs through zero. Two equations sharing the same two unknowns became two separate curves, and finding a solution that worked for both equations at once became the same thing as finding the exact point where those two curves cross each other, physically, on the page. The crossing point of two lines was now the shared solution to two relationships at once. The intersection of a curve with a straight line was now the answer to a question that could be written entirely in symbols. This is worth sitting with, because it is one of the most powerful ideas in all of mathematics, and it will help everything that follows tonight feel far more solid and visual, rather than abstract and symbolic. When you see a simple equation like y equals 2 times x plus 1, and you plot every point that makes it true, you get a straight line, sloping upward, gently, as it moves to the right, crossing the vertical number line at the point where x is 0 and y is 1. That number 1, where the line crosses the vertical axis, is called the y-intercept, and it tells you where the line begins its journey across the page. It is the starting value, the place the line occupies when the horizontal position is 0. The number 2, sitting in front of the x, is called the slope, and it tells you how steeply the line climbs. For every single step you take to the right, the line rises 2 steps upward. A bigger number there means a steeper climb. A negative number there means the line falls instead of rises as you move right. A slope of 0 means the line stays perfectly flat, never rising or falling at all, no matter how far you travel to the right or left. This single equation and this single picture actually describe an enormous number of real situations happening in your life, right now, tonight, whether you notice them or not. It describes a savings account earning simple interest, where the starting balance is your y-intercept and the amount you add each month is your slope, steadily climbing upward over time. It describes a candle burning down at a steady rate, where the starting height is your intercept and the burn rate is your slope, negative this time, since the candle grows shorter, not taller, as the hours pass. It describes the temperature in your room slowly changing after you adjusted the thermostat, drifting toward a new, steady value at a fairly constant rate, each minute bringing it closer to where it wants to settle. Any situation where something starts at a certain value and then changes by the same fixed amount over and over follows exactly this pattern. It can be described completely and precisely using this one simple equation and pictured as this one simple straight line. The line captures everything about the relationship. The intercept tells you where it begins. The slope tells you how fast it changes. And from those two numbers alone, you can predict exactly where the line will be at any point in the future, simply by extending it. But not everything in the world changes at a steady, constant rate. Some things speed up as they go. Some things slow down. Some things curve back on themselves, reversing direction entirely. And this is where the squared equations we discussed earlier come back into the picture, now with a visual shape attached to them for the very first time. When you plot every point that satisfies an equation involving a squared unknown, you do not get a straight line at all. You get a smooth, symmetric curve, shaped roughly like a bowl, or an upside-down bowl, depending on certain details of the equation. This shape is called a parabola. It is one of the most common shapes in the physical world, appearing again and again in situations where something accelerates steadily under a constant force. This is the exact shape water traces when it arcs out of a fountain, rising smoothly, slowing as it reaches its highest point, and then curving back down, pulled steadily by gravity the entire time. It is the exact path a thrown ball follows through the air, curving up, slowing, and curving back down again, tracing that same symmetrical arc. When you throw something tonight, or when you did earlier today without thinking twice about it, its path through the air was tracing out, in physical space, the solution set to a quadratic equation, the very kind of equation the Babylonians were solving with garden beds and squares 4,000 years ago, and that al-Khwarizmi solved by completing the square in 9th century Baghdad. The ball itself knows nothing of algebra, but its motion follows the rules of algebra exactly, because the rules of algebra describe the rules of how quantities change in relation to each other under constant forces. This connection between equations and shapes gives us a wonderfully intuitive way to understand what it actually means to solve an equation. If you have one equation describing one curve, and you want to know where that curve crosses the flat horizontal line marking 0, solving the equation is the same thing as finding exactly where the curve touches down onto that line. You are asking, at what points, at what values of x, does the curve reach a height of 0? A straight line crosses 0 exactly once, at a single point, unless it happens to run perfectly parallel to the 0 line, in which case it never crosses at all, or lies exactly on top of it, in which case every point along it is a solution. A parabola, that bowl-shaped curve, has more possibilities. It can cross the 0 line twice, dipping below it and then rising back up through it, giving two separate solutions. It can touch it just once, gently, at a single point, its lowest or highest point, just grazing the line, giving one repeated solution, as if the two crossing points have merged into one. Or it can miss it entirely, curving through the air above or below the line without ever touching down, giving no real solutions at all. This is not a coincidence, and it is not a separate rule you need to memorize on top of everything else. It is the exact same information as before, the number of solutions to an equation, simply made visible, turned into something you can see, rather than something you have to calculate. The geometry does not add anything new to the algebra, it simply reveals, in a different form, what the algebra already contained. The two ways of thinking are mirrors of each other, each showing the same truth from a different angle. Now let us talk about what happens when you have more than one unknown quantity tangled together in more than one relationship at the same time. This is an extremely common situation in real life, and it is where algebra shows some of its most practical power. Imagine you and a friend go to a market together, and you buy 3 apples and 2 oranges for a certain total price, and your friend buys 1 apple and 4 oranges for a different total price. Neither of you knows the individual price of an apple or an orange separately. You only know these two combined totals. You know what you paid together, and you know what your friend paid, but you do not know the price of either fruit by itself. This might feel impossible to untangle at first glance. Two unknowns, hidden inside two separate relationships, mixed together so that neither appears alone. But algebra handles this with a wonderfully clean method, one that essentially uses one equation to eliminate an unknown from the other equation entirely, collapsing the problem down to something you already know how to solve. The method is not complicated, and it follows directly from the balance scale idea we have been carrying with us all evening. Here is the idea, described gently, without diving into the arithmetic itself. If you can adjust one of the two relationships, multiplying every part of it by some careful factor, so that the amount of one particular unknown, say the oranges, matches exactly in both relationships, you can then subtract one relationship from the other entirely. When you do that subtraction, the oranges cancel out completely, vanishing from the picture, because you have engineered them to appear in exactly equal amounts on both sides. Whatever was balanced before remains balanced, but now the oranges are gone, removed equally from both sides of the scale, just as we removed weights from the balance scale earlier tonight. What is left behind is a single, simple relationship involving only the apples, exactly the kind of one unknown equation we already know how to solve. Once you know the price of an apple, you can slot that number back into either original relationship and solve for the price of an orange in turn. The second unknown reveals itself as soon as the first one is known, because the relationship between them was always there, waiting. This technique, called elimination, is one of two classic methods for solving what are called systems of equations, situations where multiple unknowns are tangled together across multiple relationships simultaneously. The other classic method, called substitution, works a little differently, but arrives at the same destination. You solve one relationship for one of the unknowns, expressing it entirely in terms of the other unknown, and then you substitute that entire expression directly into the second relationship, wherever that unknown appears. This again collapses two unknowns down into just one, solvable the same familiar way. Both methods, elimination and substitution, are really just clever, systematic ways of reducing a complicated, tangled situation down into the simple, single unknown situation we already fully understand. They use the exact same balance-based reasoning we started with at the very beginning of tonight. Nothing new is being invented. The rules are the same. You are just applying them in a slightly more organized way, keeping track of more pieces at once. And geometrically, remember, two equations, each with two unknowns, are really just two separate curves drawn on the same flat surface. Solving them together, finding the values that satisfy both relationships at once, is the same thing as finding the exact point, or points, where those two curves physically cross each other on the page. The elimination and substitution methods are just algebraic ways of finding that crossing point. The geometry shows you what the algebra is doing. The algebra gives you a way to calculate exactly what the geometry can only sketch. Two straight lines will typically cross at exactly one point, a single shared solution, unless they happen to run perfectly parallel and never meet at all, in which case there is no solution, no pair of values that satisfies both equations at once. Or unless they happen to be the exact same line drawn twice, two different equations describing the same relationship, in which case every single point along that line satisfies both relationships simultaneously, and there are infinitely many solutions. This gives you, once again, a visual, physical way of understanding an entirely symbolic process, the crossing point of two lines on a page, standing in for the shared solution to two relationships at once. There is one more foundational idea worth settling into before we move into the different branches algebra grows into, and it is the idea of a function, which is really just a formal name for a very natural, everyday kind of relationship, one you already understand intuitively, even if you have never used that word for it. A function is simply a rule that takes one number in and gives exactly one number back out every single time, with total reliability. Think of it like a vending machine. You put in a certain amount of money, you press a certain button, and you always get the exact same snack back out, every single time you make that same choice. The relationship between what you put in and what comes out is fixed, predictable, and repeatable. That is a function. The equation describing a straight line, the one we discussed earlier, with its slope and its intercept, is a function. You give it any value of x you like, and it hands you back exactly one corresponding value of y, following the same rule every time, No surprises, no exceptions. This idea of a function turns out to be one of the most useful and durable ideas in all of mathematics, because it lets you think about an entire relationship all at once as a single object, rather than thinking about individual solved points one at a time. Instead of asking, "What is the temperature at exactly 3 in the afternoon?" you can ask, "What is the function describing temperature over the whole day?" And once you have that single function in hand, you can find the temperature at any moment you like, simply by plugging that moment in and seeing what comes back out. The function is a complete description of the relationship, a machine that will answer any specific question you put to it. You do not need to solve a new equation every time. You just need the function, and then you can ask it as many questions as you like. It will answer every one of them, reliably, following its internal rule. Now, algebra also comes with a small set of consistent rules about the order in which operations should be carried out. And this matters because without an agreed order, the exact same string of symbols could mean several different things to several different people, which would make written mathematics essentially useless as a shared language. The rule, gently stated, is this: handle anything tucked inside parentheses first, since those groupings are deliberately set apart to be dealt with as their own small unit, their own miniature equation inside the larger one. Next, handle any exponents, those small numbers showing repeated multiplication. After that, handle multiplication and division, working from left to right across the expression. And finally, handle addition and subtraction, also working from left to right. This order is not arbitrary or invented for its own sake. It reflects the natural structure of how these operations build on each other. Exponents are repeated multiplication. Multiplication is repeated addition, so it makes sense to unwind them in that same layered order, from the most tightly bundled operations outward to the loosest ones. You peel the layers in the reverse order that they were applied, the same way you would unstack a pile of boxes by taking off the top one first. This consistent order is part of what allows an equation to travel, unchanged, across different countries, different languages, and different centuries, and still mean exactly the same thing to every single person who reads it. A merchant in 9th century Baghdad and a student tonight, separated by more than 1,000 years and thousands of miles, would still agree, without needing to discuss it, on exactly what a particular string of algebraic symbols means, because that order of operations has remained stable and shared for so long. There is something quietly moving about that, if you let yourself sit with it, a shared, silent agreement, stretching across 1,000 years, connecting people who will never meet. The same symbols, arranged in the same order, carrying the same meaning, generation after generation, a kind of quiet conversation, conducted across centuries, in a language that almost never changes. Now that we understand the foundation, the balance scale, the letters standing in for unknowns, completing the square, the connection to shapes and curves, and the idea of a function, let us talk about how this core idea branches outward into the different varieties of algebra that mathematicians developed once the basic tools were firmly in place. The first branch worth knowing about is simply what happens when you allow more than 2 powers into a single equation, mixing plane unknowns, squared unknowns, cubed unknowns, and beyond, all together in one expression. These are called polynomials, a word that just means many terms, and you can think of a polynomial as a kind of algebraic sentence with several clauses, each one a different power of the same unknown, all added or subtracted together. A straight line is technically the simplest possible polynomial, using only the plane unsquared power, the power of 1. A parabola uses 1 power higher, squared. As you keep adding higher and higher powers into the mix, cubed, and beyond, the resulting curves grow more elaborate, capable of curving one way and then reversing and curving the other way, sometimes several times over, tracing shapes with multiple humps and valleys as they cross the page. These higher-degree polynomials describe real, physical situations that are more complicated than simple constant growth or the smooth arc of a thrown ball. They describe the shape of sound waves layered on top of each other, the way a coastline actually curves rather than running in a perfectly straight line, and the complex paths engineers calculate when designing something like a roller coaster, where the track needs to rise, dip, curve sideways, and rise again, all in one continuous, smooth motion. Whenever a real-world curve has more than one hump or dip in it, there is very likely a higher degree polynomial quietly describing its exact shape underneath, capturing every rise and every fall in a single algebraic sentence. The scale is still level, the curves are still drawn across Descartes' flat plane, the unknown is still waiting patiently to reveal itself. And somewhere in the quiet, the balance is holding, as it always has, as it always will. Now that we understand the foundation, the balance scale, the letters standing in for unknowns, completing the square, the connection to shapes and curves, and the idea of a function, let us talk about how this core idea branches outward into the different varieties of algebra that mathematicians developed once the basic tools were firmly in place. The first branch worth knowing about is simply what happens when you allow more than two powers into a single equation, mixing plane unknowns, squared unknowns, cubed unknowns, and beyond, all together in one expression. These are called polynomials, a word that just means many terms, and you can think of a polynomial as a kind of algebraic sentence with several clauses, each one a different power of the same unknown, all added or subtracted together. A straight line is technically the simplest possible polynomial, using only the plane unsquared power, the power of 1. A parabola, that bowl-shaped curve we discussed earlier, uses one power higher, squared. As you keep adding higher and higher powers into the mix, cubed, fourth power, fifth power, and beyond, the resulting curves grow more elaborate. They become capable of curving one way and then reversing and curving the other way, sometimes several times over, tracing shapes with multiple humps and valleys as they cross the page. Imagine a gentle landscape of rolling hills, seen from the side, a line that rises to a soft peak, then dips down into a valley, then rises again to another peak, then dips again. That kind of shape, with its rises and falls, its peaks and troughs, cannot be described by a simple straight line, and it cannot be described by a simple parabola, which has only one peak or one valley. You need a polynomial with enough terms, enough different powers of the unknown, to capture each rise and each fall, each change of direction. Every time the curve reverses itself, every time it switches from climbing to falling, or from falling to climbing, you generally need another power in the polynomial. These higher-degree polynomials describe real, physical situations that are more complicated than simple constant growth or the smooth arc of a thrown ball. They describe the shape of sound waves layered on top of each other, the complex vibration of a guitar string that is not just playing one pure note, but a rich blend of harmonics, each one a different polynomial term, adding its own character to the overall shape. They describe the way a coastline actually curves, rather than running in a perfectly straight line, jagged and irregular, but still, underneath the jaggedness, following a broader shape that a polynomial can capture. They describe the complex paths engineers calculate when designing something like a roller coaster, where the track needs to rise, dip, curve sideways, and rise again, all in one continuous, smooth motion, never jerking, never jolting, each segment flowing into the next. Whenever a real-world curve has more than one hump or dip in it, there is very likely a higher-degree polynomial quietly describing its exact shape underneath. The polynomial does not care whether it is describing a sound wave, or a roller coaster, or the bending of a beam under a load. It only cares about the powers and the coefficients, the numbers sitting in front of each term, telling each power how strongly to contribute. Those coefficients are the tuning knobs of the polynomial. Adjust one, and the whole shape shifts slightly. Adjust another, and a peak moves left or right. What is quietly elegant about polynomials is that they are built from the same basic operations we have been discussing all evening: addition, subtraction, multiplication, and exponents, the small raised numbers showing repeated multiplication. Nothing more. A polynomial is just a sum of terms, each term being a number multiplied by the unknown raised to some power. Despite this simplicity, polynomials can approximate an enormous range of shapes, far more than you might expect. Given enough terms, a polynomial can trace out almost any smooth curve you can imagine, matching its rises and falls, its twists and turns, with remarkable fidelity. This fact, that polynomials can approximate nearly any smooth curve, is not just a curiosity, it is the basis for much of how computers handle complicated functions in engineering and science. When a computer needs to calculate something difficult, like the trajectory of a spacecraft through a complicated gravitational field, it often approximates the true, complex curve with a polynomial, a string of simple terms that it can evaluate very quickly, and the approximation is so close that the difference barely matters. The spacecraft still arrives exactly where it was meant to go. A second major branch involves a completely different kind of growth pattern, one where the unknown does not sit at the base being multiplied by itself, but instead sits up in the exponent position, controlling how many times a fixed number gets multiplied by itself. This is called exponential growth, and it behaves in a way that feels almost unfair compared to everything we have discussed so far tonight. In a polynomial, the unknown sits at the bottom, and the power is fixed. In an exponential, the unknown sits at the top, in the exponent, and the base is fixed. This small swap, moving the unknown from the base to the exponent, changes everything about how the relationship behaves. A polynomial grows by repeatedly adding terms of increasing power. An exponential grows by repeatedly multiplying by the same fixed factor. Exponential growth starts off deceptively slow, and then accelerates, faster and faster, without ever really slowing back down. It is patient in its early stages, almost lazy, barely distinguishable from a straight line, but then it begins to curve upward, gently at first, then more steeply, then almost vertically, as if it has been saving its energy and finally decided to spend it all at once. Picture a single grain of rice placed on the first square of a chessboard, with the rule that each following square gets double the grains of the square before it. 2 grains on the second square, 4 on the third, 8 on the fourth, 16 on the fifth. For the first several squares, this feels almost boringly modest, barely worth noticing. By the 10th square, you have 512 grains, still a small pile, easily held in 2 cupped hands. But by the 20th square, you have over 500,000 grains. By the 30th square, over 500 million. By the time you reach the final square of the board, the 64th, the number of grains required is so enormous it would outweigh anything humanity has ever harvested in its entire history, many times over. That is the strange, almost deceptive nature of exponential growth. It hides its true power in its early stages, lulling you into underestimating it, before revealing an almost incomprehensible scale later on. The curve looks flat for a long time, and then it bends upward, and then it goes nearly straight up, as if it has broken free of gravity. This pattern shows up constantly in the world around you tonight, often in places you would not necessarily connect to an algebraic equation at all. It describes how compound interest builds slowly on a savings account before accelerating meaningfully after enough years have passed. In the first few years, the growth is modest, just a little extra added to the balance. But let it run for decades, and the curve bends upward, the interest earning interest on its own interest, and the total begins to grow far faster than it ever did at the beginning. It describes how a population of bacteria in a petri dish, or a population of any organism with abundant resources and no predators, grows slowly at first and then explodes. 1 cell divides into 2, 2 into 4, 4 into 8, and for a while the numbers are manageable. But each generation doubles, and after enough generations the petri dish is full, the resources are exhausted, and the curve levels off only because the environment can no longer support it. It describes, in a different but related form, radioactive decay, running the same essential pattern backward. Instead of doubling over each fixed stretch of time, a radioactive substance halves. It loses a consistent fraction of itself over each fixed stretch of time, shrinking quickly at first, and then more and more slowly, approaching but never quite reaching zero. The curve is the mirror image of growth, falling steeply at first and then leveling out into a long, gradual decline that theoretically never ends. Doctors and scientists use this exact mathematics to determine how long a medication stays active in a person's bloodstream. If a medicine has a half-life of 6 hours, then after 6 hours half of it remains. After 12 hours a quarter remains. After 18 hours an eighth remains. The body clears it exponentially, and knowing this allows doctors to time doses so that enough medicine is always present without ever building up to dangerous levels. Archaeologists use a closely related version to determine how old an ancient object is, by measuring how much of a naturally decaying material, often a form of carbon, remains inside it. Living things take in carbon constantly while they are alive. When they die, the intake stops, and the radioactive form of carbon begins its slow exponential decay. By measuring how much is left and knowing the rate of decay, archaeologists can work backward and determine how long ago the organism died. The algebra is the same as the half-life of a medication, the same as the doubling of bacteria, the same as compound interest. The pattern is universal. A third branch worth knowing about, and one that connects directly back to those systems of equations we discussed a little earlier tonight, involves situations with far more than just two unknowns tangled together at once. Real-world problems, especially in engineering, economics, and computer graphics, frequently involve dozens, hundreds, or even millions of unknowns simultaneously, all linked together through many separate relationships at the same time. Imagine trying to predict the weather. You have temperature readings from thousands of stations, wind speed measurements, humidity levels, all collected at the same moment. Each measurement relates to the others in complicated ways. A change in temperature in one place affects the wind, which affects the humidity somewhere else, which feeds back into the temperature. Untangling all of these relationships to predict what will happen tomorrow requires handling an enormous number of unknowns, each one connected to many others through a web of relationships. Solving these by hand, one substitution or elimination at a time, would be completely impractical. You would spend a lifetime on a single forecast, and by the time you finished, the weather would have already arrived. So mathematicians developed a more organized, more compact way of writing and manipulating enormous collections of numbers all at once, called a matrix. A matrix is essentially a neat grid of numbers arranged in rows and columns that can represent an entire system of many relationships in one compact object. Instead of writing out dozens or hundreds of separate equations, you write one matrix. Then you manipulate that matrix using a small set of consistent rules, very similar in spirit to the balance scale rules we learned right at the beginning of tonight, just extended to handle many unknowns simultaneously, rather than just one or two. The rules are the same in essence. You can multiply an entire row by a number, as long as you do it to all parts of the equation that row represents. You can add one row to another, cancelling out terms, just as you cancelled out the oranges in the market problem earlier tonight. You can swap rows, rearrange them, simplify them, always following rules that preserve the underlying relationships, never disturbing the balance, only clarifying it. This branch, often called linear algebra, might sound abstract, but it is quietly doing enormous, practical work in the world around you tonight. It is what allows a video game to smoothly rotate a three-dimensional object on your screen, adjusting the position of thousands of points at once, all through a single, compact mathematical operation. When your character turns their head, or a car spins across the screen, every visible point of that object has its position recalculated, and all of those recalculations happen through matrix operations, performed in the blink of an eye. It is what allows a search engine to determine which web pages are most relevant to a particular query, essentially solving an enormous system of relationships describing how pages link to and reference one another. Each page is an unknown, and each link is a relationship, a vote of confidence from one page to another. The search engine solves the whole system at once, finding the pages that sit at the center of the web of links, the ones that are referenced most often by other highly referenced pages. It is algebra, scaled up to the size of the entire internet. It is what allows a weather forecasting model to process observations from thousands of separate weather stations simultaneously and predict how conditions will shift over the coming days. The atmosphere is divided into a grid of millions of points, each with its own temperature, pressure, humidity, and wind speed. The relationships between these points are described by a massive system of equations, and solving that system, updating every point for each time step into the future, is a job for matrices and the computers that manipulate them. Every time your phone does something that feels almost effortlessly smart, there is a very good chance that somewhere underneath, a matrix is quietly being manipulated, following rules that trace their lineage directly back to that same simple balance scale we started with, just scaled up almost unimaginably. The scale now has millions of pans, all connected, all balanced against each other simultaneously. But the principle is the same. Whatever you do to one part, you must account for in the others. The balance must hold. There is one more branch worth mentioning gently before we move on, because it represents perhaps the deepest and most unexpected direction algebra ever grew in. For most of its history, algebra was about numbers, or things that behaved essentially like numbers, unknowns standing in for specific numerical values, waiting to be solved for. But in the 1800s, mathematicians began asking a much stranger, more open question. What if you set aside numbers almost entirely, and instead studied the rules themselves, the underlying patterns of how operations behave, applying those patterns to entirely different kinds of objects that are not numbers at all? What if addition and multiplication were not about combining quantities, but about combining symmetries, or rotations, or permutations? What if the real object of study was not the things being combined, but the pattern of the combination itself? This led to what is now called abstract algebra, and its most fundamental building block is something called a group. A group is simply any collection of objects, together with one way of combining two of them to get a third, that follows a small handful of sensible rules. The objects can be anything: numbers, rotations, shuffles of a deck of cards, as long as the combination rule behaves in the right way. The rules are these. There needs to be a special object that does nothing when combined with anything else, similar to how adding 0 to a number leaves it unchanged, or how doing no rotation at all leaves an object facing the same direction. Every object needs some kind of partner that undoes it, similar to how every number has a negative version that cancels it out perfectly when added together, or how every rotation has an opposite rotation that brings you back to where you started. And the combination must be associative, meaning that if you combine three things, it does not matter which pair you combine first, as long as the order stays the same. What is quietly striking is that once mathematicians identified these underlying rules clearly, they found that groups show up almost everywhere, in situations that seem to have nothing to do with numbers at all. The different ways you can rotate and flip a square and have it still look exactly the same form a group. The different ways you can shuffle a deck of cards form a group. The symmetries of a snowflake, the 6 identical arms radiating from the center, form a group. The symmetries of a crystal, repeating in all directions, form a group. Even the strange, invisible rules governing how subatomic particles behave, worked out by physicists in the 20th century, turned out to follow the exact same mathematical patterns that mathematicians had already worked out decades earlier, studying groups purely for their own abstract elegance, with no physical application in mind whatsoever at the time. The mathematicians were not trying to explain the universe, they were simply curious about the inner logic of symmetry. And then, years later, physicists found that the particles they were studying obeyed exactly that logic, as if the universe had been written in a language that mathematicians had already learned to read. This is one of the quietest and most moving facts in the entire history of mathematics. a pattern studied purely out of curiosity, with no application intended, later turned out to describe something true and fundamental about the physical structure of the universe itself, found independently by physicists who had no idea mathematicians had already mapped out the territory generations before them. The mathematicians were like explorers who drew maps of a continent they had never visited, and then, years later, travelers arrived there and found that the maps were accurate in every detail. The unknown does not always reveal itself on our schedule. Sometimes we work out the rules first, purely for the sake of understanding the rules, and only much later do we find what those rules were describing all along. The balance holds, the pattern waits, and somewhere, quietly, a matrix is turning, a polynomial is bending, an exponential curve is beginning its long, patient climb upward, and a group of symmetries is holding a snowflake together, exactly as it has for billions of winters before anyone ever thought to name it. Let us bring this back down now, out of the abstract heights, and settle into where all of this actually lives, quietly, in the room around you tonight, and in the ordinary shape of your day. Your phone, resting somewhere nearby, is running algebra constantly, in layers stacked on top of layers. Every single second it is powered on. The screen you might have looked at earlier tonight displays images built from millions of tiny colored points, each one a small square of light, and adjusting the brightness, the color balance, or the size of anything on that screen involves solving small systems of linear equations, the same elimination and substitution methods we discussed earlier, just performed automatically, billions of times per second, far faster than any human hand ever could. When you swipe your finger across the screen and the image slides smoothly under your touch, matrices are being multiplied behind the scenes, recalculating the position of every visible point so quickly that you perceive no delay at all. The smoothness of that motion, the way the image glides rather than jerks, is a direct result of linear algebra, the same branch of mathematics that helps rotate three-dimensional objects in video games and simulations. Every time you pinch to zoom, every time a photo resizes itself to fit the frame, a small system of equations is being solved, updating the coordinates of millions of pixels in a fraction of a heartbeat. When a map application calculated the fastest route somewhere today, it was essentially solving a massive system of relationships describing distances and travel times across an entire network of roads. Each intersection is a point. Each road segment is a connection with a weight, the time it takes to travel it. Finding the fastest route means searching through an enormous web of possibilities, balancing distance against time, against traffic conditions, and the algorithm that does this is solving a kind of equation, not a single equation with a single unknown, but a vast network of them, all balanced simultaneously. The same underlying spirit as balancing that scale with the unknown bag of weights, just extended across an entire city, across millions of roads and intersections, solved in the time it takes you to glance at the screen. When that same phone connects to a wireless network, or to the cellular tower a few miles away, the signal it sends and receives is processed using algebra that goes back to the work of a French mathematician named Joseph Fourier, who lived in the late 1700s and early 1800s. Fourier worked out that any repeating signal, any wave shape, no matter how complicated, can be broken down into a sum of simple, smooth waves, each with its own frequency and its own strength. This decomposition, now called the Fourier transform, is a piece of algebra that your phone performs constantly, breaking down incoming radio waves into their component frequencies, filtering out noise, isolating the signal that carries the voice or the data, and then reassembling everything on the other end. Every phone call, every text message, every video streamed to your screen tonight relies on this same algebraic idea, this same insight that a complicated wave is just a sum of simpler ones. Your body, resting right now, is itself full of relationships that follow these same patterns. The way medication moves through your bloodstream and gradually clears out follows that same exponential decay pattern we discussed earlier tonight. Doctors calculating dosages and timing using exactly this mathematics. ensuring enough of a medicine stays active in your system without ever letting it build up to unsafe levels. If you have ever taken a prescription that required a specific schedule, 1 pill every 6 hours, 1 dose every morning, the timing was determined by the exponential decay curve of that particular medication, worked out through careful measurement and then described with an algebraic equation that predicts exactly how much remains in your bloodstream at any given moment. The rhythm of your own heartbeat, if you were to graph it precisely over time, traces out a repeating wave pattern that mathematicians describe using equations with a close family relationship to the polynomial curves we discussed earlier. It repeats smoothly, predictably, the same essential shape over and over as long as you live. A small electrical wave moving through the muscle of your heart, triggering each beat in sequence. That wave can be broken down, using Fourier's idea, into a sum of simpler waves, and doctors can look at those simpler components to detect problems, irregularities that are invisible in the overall shape, but clear in the breakdown. The building around you tonight, whatever room you happen to be resting in, was almost certainly designed using algebra at nearly every stage. An architect calculating how much weight a beam can safely support before it bends is solving equations describing the relationship between material strength, length, and load. The beam across the ceiling above you, if you could see it through the plaster and paint, was sized according to these calculations. Too small, and it would sag or crack. Too large, and the building would be unnecessarily heavy and expensive. The right size, the balanced size, was found by solving an equation. An electrician wiring the room you are in used equations relating voltage, current, and resistance, a beautifully simple algebraic relationship that governs every single electrical device quietly running in your home tonight, from a phone charger to a refrigerator humming in another room. That relationship, often called Ohm's law, states that the current flowing through a wire is equal to the voltage divided by the resistance. It is an equation of the very simplest kind, just 3 quantities in a fixed relationship, and from it, every wire in your home is sized to carry the expected load safely, without overheating, without wasting energy. Every switch, every outlet, every circuit breaker is rated according to algebra, worked out carefully long before anyone ever moved in, so that the lights turn on reliably every single time you ask them to. The water pipes in the walls, if we could see them, were sized using a different set of equations, but the principle is the same. The flow of water through a pipe depends on the pressure, the diameter of the pipe, the length of the run, and the roughness of the interior surface. All of these factors fit together into an algebraic relationship, and solving that relationship tells the engineer what diameter pipe to install so that the shower has enough pressure and the sink fills quickly and the toilet flushes completely. None of this is guesswork. It is algebra, applied quietly, invisibly, reliably. Even something as unremarkable as a recipe, if you cooked anything today, involves a quiet form of algebraic reasoning. Scaling every ingredient up or down proportionally to serve a different number of people is exactly the kind of proportional reasoning the ancient Egyptians were already comfortable with, using their method of false position 4,000 years before tonight. If a recipe calls for 2 cups of flour to serve 4 people, and you need to serve 6, you are solving a simple proportion, whether you write it down or not. You are finding the missing quantity, the unknown amount of flour, by balancing the ratio of flour to people against the known amounts. It is algebra, in its oldest and most intuitive form, performed without symbols, without notation, just the quiet recognition that proportions must balance. The music you might have heard today, in the car, in a shop, playing softly somewhere in the background, is built on algebraic relationships. The notes of a scale are not chosen arbitrarily. They follow mathematical ratios, frequencies that stand in simple fractional relationships to one another. An octave is a doubling of frequency. A perfect fifth is a ratio of 3 to 2. A perfect fourth is a ratio of 4 to 3. These simple fractions, these clean algebraic relationships, are what make certain combinations of notes sound pleasant, and others sound tense or jarring. When a composer writes a harmony, when a guitarist tunes their strings, when a piano tuner adjusts the tension on each wire, they are working with the algebra of frequencies, whether they think of it in those terms or not. And above you, whether you can see it through a window right now or not, the sky itself runs on algebra, on a grand and ancient scale. The paths of planets, the timing of tides pulled by the moon, the precise moment the sun will rise tomorrow morning, all of these are calculated using equations that trace their lineage directly back through Descartes, through al-Khwarizmi, through those careful Babylonian scribes pressing symbols into wet clay beside their two great rivers. The motion of the planets was one of the great drivers of algebraic development for centuries. Kepler, working in the early 1600s, analyzed decades of planetary observations and found that the orbits were not perfect circles, as had been assumed for centuries, but ellipses, slightly squashed circles, and he found algebraic relationships that described exactly how fast each planet moved at each point in its orbit. A planet moves faster when it is closer to the sun, and slower when it is farther away, and the relationship between its distance and its speed follows a precise algebraic law. Kepler expressed these laws in words and proportions, but later astronomers and physicists translated them into equations, and those equations are still used today. Every time a spacecraft is sent to another planet, every time an astronomer predicts where a comet will appear in the sky. The tides, rising and falling against the shore, follow a pattern that can be described algebraically, a combination of several different cycles: the daily rotation of the Earth, the monthly orbit of the Moon, the yearly orbit of the Earth around the Sun, all layered on top of each other, each contributing its own wave, and the sum of all those waves, the combined tide, predicted accurately years in advance using the same kind of Fourier analysis that your phone uses to process a wireless signal. The same algebra that brings a voice to your ear brings the ocean to the shore and then draws it back again, on schedule, every single time. Astronomers tonight, in observatories scattered across the world, are pointing instruments at distant points of light and using algebra to determine how far away those lights actually are, how fast they are moving, and in some cases, whether anything might be orbiting around them. The light from a distant star is analyzed by passing it through a prism or a grating, spreading it out into a rainbow, a spectrum. That spectrum contains dark lines, specific wavelengths where elements in the star's atmosphere have absorbed some of the light. The positions of those lines reveal what the star is made of. The shift of those lines toward the red or the blue reveals how fast the star is moving toward us or away from us, and the relationship between the shift and the speed is an algebraic one, a simple proportion, the same kind of proportion the ancient Egyptians used, now applied to light from a star so far away that it has been traveling toward us for millions of years. The same fundamental method, an unknown quantity, treated as if it were known, isolated patiently through careful, balanced steps, is being used tonight to measure distances so vast they are almost impossible to hold in your mind, and it is also being used, at the exact same moment, by a student somewhere solving a simple homework problem about apples and oranges at a market. The scale of application ranges from the size of a grocery bag to the size of the visible universe, and underneath both, it is genuinely the exact same idea, applied with the exact same quiet patience. The unknown is the unknown, whether it is the price of a single apple or the distance to a galaxy. The method for finding it does not change. You write down what you know, you give a name to what you do not know, and you work backward, step by step, never disturbing the balance, only clarifying it, until what was hidden reveals itself. The student and the astronomer are doing the same thing. They are separated by the scale of their problems, but united by the method they use to solve them. The traffic lights you drove past today operate on timers and sensors that involve algebraic logic, calculating how long each light should stay green to keep traffic flowing smoothly, balancing the needs of different directions of travel against each other, solving a kind of equation where the unknowns are the wait times and the constraints are the traffic volumes. The engineers who designed those intersections used algebra to determine the timing patterns, and the controllers that run the lights are solving small versions of those equations constantly, adjusting to the flow of cars as it changes through the day. The heating or cooling system in your room, if you have one, uses a thermostat that measures the current temperature, compares it to the desired temperature, and calculates how much heating or cooling to apply. That calculation is based on a kind of equation called a control equation, and it balances the need to reach the target temperature against the need to avoid overshooting, to avoid wasting energy, to keep the room comfortable without constant swings between too hot and too cold. The thermostat is constantly solving for the right amount of adjustment, the same way you might adjust a balance scale, a little more on this side, a little less on that, until it settles perfectly level. The screen you are not looking at right now, because your eyes are closed, or nearly closed, displays text and images using algorithms that decide how to arrange everything on the screen, how much space to leave between lines, how to wrap text at the end of a line, how to scale an image to fit the available space. Every one of those decisions involves algebraic calculations, proportions and ratios and scaling factors, performed so quickly and so often that they are invisible to you, part of the seamless experience of using a device. You do not notice the algebra because it is doing its job perfectly, quietly, without drawing attention to itself. The encryption that protects your bank account when you check your balance, that protects your messages when you send them, that protects any private information you might have transmitted today, relies on algebra of a different and more modern kind, involving very large prime numbers and the difficulty of factoring them back into their components. The security of your information rests on the fact that multiplying two large prime numbers together is easy and fast, but taking the resulting enormous number and figuring out which two primes were multiplied to make it is so difficult that even the most powerful computers in the world would need longer than the age of the universe to do it. This asymmetry, easy one way and nearly impossible the other way, is the foundation of modern cryptography, and it is built on number theory, a close cousin of algebra, concerned with the properties of whole numbers and the relationships between them. All of this is happening around you, and inside the devices around you, and inside the devices around you, and inside your own body, all the time, whether you are paying attention to it or not. Algebra is not something that lives only in textbooks and classrooms. It is a quiet, persistent, invisible thread running through almost every aspect of modern life, from the way your food is packaged, to the way your messages are delivered, from the way your heart beats, to the way the planets move. And yet, for all of this, algebra asks very little of you tonight. It does not demand that you solve anything. It does not require you to remember any formulas or practice any techniques. It is simply there, running quietly in the background, the same way your own body is balancing its chemicals, adjusting its temperature, keeping everything level and steady without your conscious involvement. The scale is level. The unknown is still there, but it is being solved for, constantly, by processes that do not need your attention. You can let them run. You can let everything balance itself, as it has been doing all along, long before you ever heard the word algebra, and long after you have drifted off to sleep. The equations will keep working, quietly, faithfully, keeping everything in balance, finding everything that is missing, the way they always have. Now let us turn, gently, to some of the harder questions, the parts of this subject that still genuinely puzzle mathematicians, or that carry a strangeness worth sitting with quietly before we bring everything together. Remember those methods for solving cubic and fourth-degree equations, worked out by competitive Italian mathematicians centuries ago. Those were genuine triumphs, hard-won solutions that required real cleverness, real persistence. For a long time after those findings, mathematicians assumed that equations involving even higher powers, the fifth power and beyond, would eventually yield to some similarly clever, if more elaborate, general formula, if only someone worked hard enough and cleverly enough to find it. It seemed like just a matter of time and effort. The pattern so far had been that each new degree of complexity required a new level of ingenuity, but that ingenuity was always found eventually. Many brilliant people spent years of their lives searching for exactly this, a general formula for solving equations involving the fifth power. They tried extending the methods that had worked for cubic and quartic equations. They tried inventing entirely new methods. They tried clever substitutions, geometric approaches, analogies to other branches of mathematics. Year after year, the problem remained unsolved, but the assumption was always that the solution was out there, waiting, and that someone, eventually, would be clever enough to find it. And then, in the early 1800s, a young mathematician named Niels Henrik Abel, working largely alone in Norway, far from the main centers of European mathematical life, managed to prove something genuinely strange. He proved that no such general formula could ever exist, for equations involving a fifth power or higher. Not that nobody had found it yet, not that it was simply difficult or required more time. He proved, with complete mathematical certainty, that it was fundamentally, permanently impossible for a formula of that type to exist at all. This is a different kind of result than anything we have discussed so far tonight. Most of the history we have walked through involves clever people eventually finding a way through a difficult problem, given enough time and insight. The Babylonians found completing the square. Al-Khwarizmi found the general classification of quadratic equations. The Italian mathematicians found the cubic and quartic formulas. Each time, the wall turned out to have a door, and someone found the key. This result says something different. It says that some problems have walls around them, not walls built from lack of cleverness, but walls built into the actual structure of mathematics itself, permanent, and no amount of future genius will ever tear them down. It is not that we are not smart enough yet, it is that the thing we were trying to do is impossible in principle, like trying to find a largest prime number, or trying to draw a four-sided triangle. Abel's proof was not a statement about human limitations. It was a statement about the nature of the problem itself. Using a certain set of tools, addition, subtraction, multiplication, division, and the taking of roots, you can solve any equation up to the fourth degree with a general formula. For the fifth degree and beyond, those tools are simply not enough. They cannot, even in principle, be enough. You would need a different kind of tool entirely. There is something almost peaceful in that, if you let yourself sit with it a moment. Not every unsolved question is a temporary gap waiting to be filled. Some are settled, finally and completely, in the negative, and that, too, is a form of genuine understanding. Knowing that something is impossible is a real piece of knowledge. It tells you to stop looking in that direction and turn your attention elsewhere. It tells you something true about the shape of the world. Around the same time, another young mathematician, Évariste Galois, working in France, developed an even deeper understanding of why some equations could be solved with simple formulas and others could not. Galois was barely in his 20s, and his life was cut short in a duel, a story so dramatic it almost feels invented, but his mathematical ideas, scribbled in a letter the night before the duel, turned out to contain the seeds of an entirely new way of thinking about equations. Galois realized that the solvability of an equation was tied to the symmetries of its solutions. If you take the solutions to an equation and shuffle them around, some shuffles preserve the algebraic relationships between the solutions, and some do not. The set of shuffles that preserve the relationships forms a group, in the sense we discussed earlier, a collection of symmetries with a rule for combining them. Galois showed that an equation can be solved with a simple formula if and only if its group of symmetries has a certain kind of structure, a structure that can be broken down step by step in a particular way. For equations of degree 4 and below, the groups always have this structure. For degree 5 and above, they generally do not. The reason the quintic equation cannot be solved by a general formula is not that mathematicians were not clever enough. It is that the symmetries of the 5 solutions are too tangled, too interconnected, to be untangled by the simple operations of addition, multiplication, and the taking of roots. The group itself resists being broken down. This is a deeply elegant idea, and it connects algebra to symmetry in a way that had never been seen before. An equation is not just a string of symbols. It is a kind of symmetric object with a hidden structure that determines what can and cannot be done with it. Solving an equation is not just a matter of manipulation. It is a matter of understanding the symmetries of the unknown quantities and how they relate to each other. Galois did not live to see his ideas accepted. The mathematical community of his time was not ready for them. But his letter, passed through the hands of a friend, eventually made its way to mathematicians who could understand it, and today the theory that bears his name, Galois theory, is a central part of abstract algebra. It connects the study of equations to the study of groups, and it explains, once and for all, why some equations yield to simple formulas and others do not. There is another quiet strangeness worth mentioning, involving numbers that come from finding what number, multiplied by itself, gives you a negative result. Ordinary numbers, whether positive or negative, always give a positive result when multiplied by themselves. A positive number times itself is positive. A negative number times itself is also positive, because a negative times a negative gives a positive. This means that, within the ordinary numbers you use every day, no number exists that could ever multiply by itself to produce a negative answer. If you try to find the square root of -1, you are asking a question that has no answer in the ordinary number system. And yet, mathematicians found genuine, practical use in imagining what such a number would behave like anyway, giving it a name, and working out consistent rules for how it interacts with everything else. They called this number I, for imaginary, and they treated it as a new kind of unit, perpendicular in some sense to the ordinary number line. These are called imaginary numbers, a slightly unfortunate name, coined originally almost as an insult by a mathematician who doubted they were legitimate at all, and the name simply stuck, even after these numbers turned out to be genuinely essential, not just a curiosity. The name makes them sound made up, fictional, not quite real. But in truth, they are no more imaginary than negative numbers, which also once seemed like nonsense. How can you have -3 apples? But we got used to negative numbers, and now they feel natural. The same thing happened with imaginary numbers, though the name never caught up with the reality. Imaginary numbers show up centrally in how engineers describe alternating electrical current. The current in your home wiring alternates, switching direction many times per second, and describing that oscillation mathematically requires imaginary numbers. Without them, the calculations would be far more cumbersome, far less elegant. With them, the behavior of alternating current becomes clean and predictable. They show up in how physicists describe the strange behavior of particles at the smallest scales. Quantum mechanics, the theory that governs the behavior of atoms and subatomic particles, is written in a mathematical language that relies heavily on imaginary numbers. The fundamental equation of quantum mechanics contains I, explicitly. Without imaginary numbers, the theory would be almost impossible to express in its current form. They show up in signal processing software that cleans up audio recordings, removing noise, isolating voices, compressing music into smaller files without losing too much quality. The mathematics behind these techniques works most naturally when you allow imaginary numbers into the picture. They are not a gimmick, they are a tool, and an extremely effective one. Something that began as a kind of mathematical fiction, a number nobody could quite believe in, turned out, generations later, to be quietly running through the electrical wiring in the walls around you right now, and through the physics that makes that wiring work in the first place. Together, ordinary numbers and imaginary numbers form what are called complex numbers, a combination of a real part and an imaginary part. Complex numbers have a rich and beautiful structure. They can be plotted on a plane, the complex plane, with the real part on one axis and the imaginary part on the other. Every algebraic equation, no matter how complicated, has a solution somewhere in the complex numbers. This is the fundamental theorem of algebra, and it says that the complex numbers are, in a sense, the natural, complete number system for algebra. You never need to invent anything new. The answers are always there, somewhere in the complex plane, waiting to be found. By now you may have drifted in and out a few times. That is exactly right. There is nothing to catch up on. Everything has been settling quietly whether you were following closely or not. The way rain settles into soil, whether or not anyone is watching it happen. The equations do not need you to pay attention. They keep working either way. The balance keeps holding either way. The unknown keeps waiting, patiently, to be found. By now you may have drifted in and out a few times. That is exactly right. There is nothing to catch up on. Everything has been settling quietly, whether you were following closely or not. The way rain settles into soil, whether or not anyone is watching it happen. The ideas do not need your attention to be true. They were true before you heard them, and they will be true long after you have fallen asleep. If you were to hold all of tonight in one single image, it would be this. A scale, old and simple, hanging perfectly level. One pan holding something known, the other holding something hidden, wrapped in a plain cloth bag. And a patient hand, reaching in again and again, removing the exact same small amount from both sides at once, never disturbing the balance, only simplifying it, step by careful step, until finally, quietly, the cloth bag sits alone on its pan, and its weight is known. That is what algebra has been, this entire time, underneath every layer we added tonight. Not a set of rules to memorize, not a collection of symbols to decode, but a patient method, a quiet way of thinking, a way of treating something unknown as if it were known, giving it a name, and then working backward through fair moves until it reveals itself. The Babylonians used it to divide land fairly along two ancient rivers. They pressed their styluses into wet clay and wrote out problems in full sentences, no symbols, no shorthand, just careful language describing a process. They worked out how to complete the square by imagining garden beds and strips of land, rearranging them into perfect shapes that could be measured. They did not call it algebra. They did not have a name for what they were doing, but they were doing it, and it worked, and the tablets they left behind still carry the marks of their reasoning, pressed into clay that has survived 4,000 years. Al-Khwarizmi gave it a name in a city built as a monument to learning. Baghdad in the 9th century, the House of Wisdom, where scholars from many cultures gathered and translated and argued and built on each other's work. He wrote a book that classified every type of quadratic equation and gave a guaranteed method for solving each one. He called his method Algebra, completion, the act of restoring balance by moving quantities from one side to the other. That word traveled through translations and centuries and languages until it became algebra, the name we use tonight. And his own name, al-Khwarizmi, traveled a different path and became algorithm, the word for any step-by-step procedure, any reliable method for solving a problem. He showed that one method could solve an entire family of problems at once, not just a single one. That was the leap. Not finding the answer to one particular puzzle, but finding a way to solve every puzzle of that shape, forever, no matter what numbers appeared in it. The method generalizes completely. That is what makes it algebra, and not just arithmetic. Descartes gave it a picture. Lying in bed, watching a fly crawl across his ceiling, he realized that two numbers could pin down any point on a flat surface, and that an equation with two unknowns could be drawn as a curve, a shape, something visible. Algebra and geometry, which had grown up separately for thousands of years, were suddenly revealed to be two views of the same truth. An equation was a shape was an equation. Solving an equation meant finding where a curve crossed a line, and two equations together meant finding where two curves crossed each other. The symbolic and the visual became one. Mathematicians gave it letters for the unknown and the known both, so that a single written line could describe every possible version of a problem, rather than just one. Viete used vowels for unknowns and consonants for knowns. Descartes refined it further, settling on X, Y, and Z for the things you do not know, and A, B, and C for the things you do. Small raised numbers, exponents, showed how many times a quantity was multiplied by itself. The notation became stable, shared, a language that could travel across countries and centuries without losing its meaning. They extended it to handle negative numbers, which once seemed like nonsense. How can you have less than nothing? What would negative 3 apples look like, sitting on a table? But mathematicians in India understood that negative numbers were not nonsense at all. They represented debt or direction or a deficit, something perfectly sensible once you stopped insisting that every number had to be a pile of objects you could hold in your hand. Brahmagupta wrote the rules for how negative numbers behave, and once they were accepted, algebra became truly general, truly universal, applying the same rules everywhere without needing special cases for positive and negative. They extended it to numbers that seemed even stranger, imaginary numbers, the square roots of negative quantities. These began as a kind of mathematical fiction, a number nobody could quite believe in, named almost as an insult. But they turned out to be essential, appearing in the equations that describe alternating current in your home wiring, in the quantum mechanics that governs the behavior of subatomic particles, in the signal processing that cleans up audio and compresses music. Something that began as a curiosity, a what-if, became indispensable. They extended it, eventually, to patterns so abstract they no longer describe numbers at all, only the pure shape of how symmetry and structure behave. Groups, the symmetries of a square, the shuffles of a deck of cards, the symmetries of a snowflake, all following the same small set of rules, the same underlying logic. And those patterns, studied purely out of curiosity, with no application in mind, turned out to describe the deepest workings of physical reality itself, the rules governing subatomic particles, found by physicists who had no idea mathematicians had already mapped out the territory generations before them. And through every single one of those layers, every century, every civilization, every notation change, the core idea never once changed. Something is hidden, something else is known, and there exists a patient, careful, repeatable way of moving from one to the other, a set of fair moves that never disturbs the balance, only clarifies it, until what was hidden finally, quietly, reveals itself. The Babylonian scribe dividing an inheritance fairly beside the Euphrates, the student in Baghdad working through al-Khwarizmi's 6 types of equations, the Italian mathematician in the Renaissance, guarding his cubic formula like a trade secret before a public contest, Descartes in his bed, watching a fly and seeing the connection between equations and curves, Abel in Norway, proving that some equations would never yield to simple formulas, no matter how clever anyone became, Wiles in his attic study, working in secret for years to prove a theorem that had waited 3 centuries for a proof. All of them were doing the same thing, in different ways, with different tools, at different scales. They were looking at something unknown, treating it as if it were known, and then working backward, patiently, carefully, never disturbing the balance, only clarifying it, until the unknown had no choice but to reveal itself. You have been doing a version of this your entire life, long before you ever saw a letter used to stand in for a number. Every time you noticed that something did not add up and worked backward, carefully, to figure out what was missing, you were practicing algebra, in its oldest and truest sense. Every time you adjusted a recipe for a different number of people, every time you figured out how much time you needed to leave to arrive somewhere by a certain hour, every time you balanced your spending against your income, or divided a bill fairly among friends, or estimated how much paint you needed to cover a wall, you were solving for an unknown, using what you knew to find what you did not, long before anyone gave it that name in a city beside 2 rivers, a very long time ago. Algebra is not foreign to you. It is not something that lives only in textbooks and classrooms, accessible only to a certain kind of mind. It is a formal version of something you already do, naturally, without thinking about it. The textbook version adds symbols and systematic methods and general formulas, but the underlying instinct, the sense that something is missing and can be found by careful, balanced reasoning, is already there, already part of how you move through the world. The scale is the right image for this. Not a machine, not a computer, not anything complicated. Just a simple balance, two pans, a central point, and the quiet understanding that whatever you do to one side, you must do to the other. That is the whole ethic of algebra: fairness, balance, patience. The refusal to force an answer by breaking the rules, the willingness to wait, to work step by careful step, until the unknown reveals itself on its own terms. And that same ethic, that same patience, is what your body is practicing right now, as you lie there in the dark. Your brain is balancing chemicals, adjusting the mixture, shifting the scale slightly towards sleep, then back, then towards sleep again, until eventually it will tip all the way and you will drift off without even noticing the moment it happened. You do not have to solve for anything tonight. You do not have to isolate any unknown or bring anything into balance on purpose. It is already happening, on its own, the way it always has, the way it will keep happening long after your thoughts have gone quiet and drifted somewhere else entirely. The scale is level. It has been level for a while now, and soon, very soon, you will let go of it completely and rest. Here is Section 8, continuing from Section 7 and following the blueprint toward the closing sections. By now you may have drifted in and out a few times. That is exactly right. There is nothing to catch up on. Everything has been settling quietly, whether you were following closely or not. The way rain settles into soil, whether or not anyone is watching it happen. The ideas do not need your attention to remain true. They were true before you heard them, and they will be true long after tonight has faded into a distant memory. If you were to hold all of tonight in one single image, if you were to compress everything we have walked through into a picture you could hold in your mind without effort, it would be this: a scale, old and simple, the kind with two pans hanging from a horizontal bar, resting on a central point, perfectly level, perfectly still. One pan holds something known, a collection of weights whose value you can read clearly. The other holds something hidden, wrapped in a plain cloth bag, its weight unknown, its contents a mystery. And a patient hand, reaching in again and again, removing the exact same small amount from both sides at once, never disturbing the balance, never tipping the scale one way or the other, only simplifying the picture, step by careful step, until finally, quietly, the cloth bag sits alone on its pan, everything else has been removed, and its weight is known. Not guessed, not approximated, known with complete certainty, because the balance was never broken. That is what algebra has been, this entire time, underneath every layer we added tonight. Not a set of rules to memorize, not a collection of symbols to decode, not a subject you either have a talent for or do not. It is a method, a quiet way of thinking, a way of treating something unknown as if it were known, giving it a temporary name, a placeholder, and then working backward through fair moves until the placeholder reveals its true value. The method does not change, the scale does not change. Only the complexity of what sits on the pans changes. The Babylonians used this method to divide land fairly along two ancient rivers. They pressed their styluses into wet clay and wrote out problems in full sentences, no symbols, no shorthand, just careful, repeated language describing a process they understood deeply. They worked out how to complete the square by imagining garden beds and strips of land, rearranging them into perfect shapes that could be measured directly. They did not call what they were doing algebra. They did not have a name for it at all. But they were doing it, and it worked, and the tablets they left behind, baked hard by fires that destroyed the libraries that held them, still carry the marks of their reasoning, pressed into clay that has survived 4,000 years of wind and sand and the rise and fall of empires. Al-Khwarizmi gave the method a name, in a city built as a monument to learning. Baghdad in the 9th century, the House of Wisdom, where scholars from many cultures gathered and translated and argued and built on each other's work, where Greek geometry met Indian arithmetic, met Babylonian calculation methods, all of it woven together into something new. He wrote a book that classified every type of quadratic equation and gave a guaranteed method for solving each one, not just a collection of worked examples, but a complete system, a menu of equation types and the method for each. He called his central operation Algebra, completion, the act of restoring balance by moving quantities from one side of an equation to the other. That word traveled through translations and centuries and languages, through Latin and Italian and French and English, until it became algebra, the name we use tonight. And his own name, al-Khwarizmi, traveled a different path, through a different chain of translations and mispronunciations, and became algorithm, the word for any step-by-step procedure, any reliable method for solving a problem, whether that problem involves numbers or recipes or the code running inside your phone. He showed that one method could solve an entire family of problems at once, not just a single one. That was the leap. Not finding the answer to one particular puzzle, but finding a way to solve every puzzle of that shape, forever, no matter what numbers appeared in it. The method generalizes completely. That is what makes it algebra, and not just arithmetic. That is what makes it a science and not just a collection of tricks. Descartes gave the method a picture. Lying in bed, watching a fly crawl across his ceiling, he realized that two numbers could pin down any point on a flat surface, and that an equation with two unknowns could be drawn as a curve, a shape, something visible to the eye. Algebra and geometry, which had grown up separately for thousands of years, each with their own tools and traditions, were suddenly revealed to be two views of the exact same truth, two languages describing the same reality. An equation was a shape. A shape was an equation. Solving an equation meant finding where a curve crossed a line, and two equations together meant finding where two curves crossed each other. The symbolic and the visual became one, and mathematics has never been the same since. Mathematicians gave the method letters for the unknown and the known both, so that a single written line could describe every possible version of a problem, rather than just one specific instance. Viet used vowels for unknowns and consonants for knowns, the first time anyone had written an equation in a fully general form. Descartes refined the notation further, settling on the convention we still use tonight: X, Y, and Z for the things you do not know, A, B, and C for the things you do. Small raised numbers, exponents, showed how many times a quantity was multiplied by itself. The notation became stable, shared, a language that could travel across countries and centuries without losing its meaning, so that a merchant in 9th century Baghdad and a student tonight, separated by more than 1,000 years and thousands of miles, would still agree, without needing to discuss it, on exactly what a particular string of symbols means. They extended the method to handle negative numbers, which once seemed like nonsense, a fantasy, an impossibility. How can you have less than nothing? What would -3 apples look like, sitting on a table? But mathematicians in India, working independently of the European tradition, understood that negative numbers were not nonsense at all. They represented debt or direction or a deficit, something perfectly sensible once you stopped insisting that every number had to be a pile of physical objects you could hold in your hand. Brahmagupta wrote the rules for how negative numbers behave in addition, subtraction, and multiplication. And once those rules were accepted, algebra became truly general, truly universal, applying the same methods everywhere, without needing special cases carved out for positive and negative separately. They extended it to numbers that seemed even stranger, imaginary numbers, the square roots of negative quantities. These began as a kind of mathematical fiction, a number nobody could quite believe in, given a name that was originally almost an insult, a dismissal. But they turned out to be essential, genuinely essential, showing up in the equations that describe alternating current in your home wiring, in the quantum mechanics that governs the behavior of subatomic particles, in the signal processing that cleans up audio recordings and compresses music into smaller files. Something that began as a curiosity, a what-if, became indispensable, quietly running through the walls around you tonight. They extended it, eventually, to patterns so abstract they no longer describe numbers at all, only the pure shape of how symmetry and structure behave. Groups, the symmetries of a square, the shuffles of a deck of cards, the symmetries of a snowflake, all following the same small set of rules, the same underlying logic of combination and reversal and identity. And those patterns, studied purely out of curiosity, with no application in mind, turned out decades later to describe the deepest workings of physical reality itself. The rules governing subatomic particles, found by physicists who had no idea mathematicians had already mapped out the territory generations before them. And through every single one of those layers, every century, every civilization, every notation change, the core idea never once changed. Something is hidden, something else is known, and there exists a patient, careful, repeatable way of moving from one to the other, a set of fair moves that never disturbs the balance, only clarifies it, until what was hidden finally, quietly, reveals itself. The Babylonian scribe dividing an inheritance fairly beside the Euphrates. The student in Baghdad working through al-Khwarizmi's 6 types of equations by lamplight. The Italian mathematician in the Renaissance, guarding his cubic formula like a trade secret before a public contest. Descartes in his bed, watching a fly and seeing for the first time that an equation could be a picture. Abel in Norway, proving that some equations would never yield to simple formulas, no matter how clever anyone became. Wiles in his attic study, working in secret for 7 years to prove a theorem that had waited 3 centuries for a proof. All of them were doing the same thing, in different ways, with different tools, at different scales. They were looking at something unknown, treating it as if it were known, and then working backward, patiently, carefully, never disturbing the balance, only clarifying it, until the unknown had no choice but to show itself. You have been doing a version of this your entire life, long before you ever saw a letter used to stand in for a number. Every time you noticed that something did not add up, and worked backward carefully to figure out what was missing, you were practicing algebra, in its oldest and truest sense. Every time you adjusted a recipe for a different number of people, scaling the flour and the sugar and the butter proportionally, every time you figured out how much time you needed to leave to arrive somewhere by a certain hour, working backward from the arrival time through the expected traffic and the stops along the way. Every time you balanced your spending against your income, or divided a bill fairly among friends, or estimated how much paint you would need to cover a wall, you were solving for an unknown, using what you knew to find what you did not, long before anyone gave it that name in a city beside 2 rivers, a very long time ago. Algebra is not foreign to you. It is not something that lives only in textbooks and classrooms, accessible only to a certain kind of mind. It is a formal version of something you already do, naturally, without thinking about it. The textbook version adds symbols and systematic methods and general formulas, but the underlying instinct, the sense that something is missing and can be found by careful, balanced reasoning, is already there, already part of how you move through the world, already part of how you have always moved through the world. The scale is the right image for this, the truest image. Not a machine, not a computer, not anything complicated or modern, just a simple balance, 2 pans, a central point, and the quiet understanding that whatever you do to one side, you must do to the other. That is the whole ethic of algebra. Fairness, balance, patience, the refusal to force an answer by breaking the rules, the willingness to wait, to work step by careful step, until the unknown reveals itself on its own terms, not forced, not guessed, but found. And that same ethic, that same patience, is what your body is practicing right now, as you lie there in the dark. Your brain is balancing chemicals, adjusting the mixture, shifting the scale slightly towards sleep, then back, then towards sleep again, until eventually it will tip all the way, and you will drift off without even noticing the moment it happened. You do not have to solve for anything tonight. You do not have to isolate any unknown or bring anything into balance on purpose. It is already happening, on its own, the way it always has, the way it will keep happening long after your thoughts have gone quiet and drifted somewhere else entirely. The scale is level. It has been level for a while now, and soon, very soon, you can let go of it completely and rest. Let us close now, gently, the way this whole night has moved, unhurried, the way water moves when nothing is pushing it anywhere in particular. Somewhere in your body right now, something is still quietly balancing, warmth against cool air, the temperature of your skin adjusting to the temperature of the room, a small, steady exchange, heat flowing outward, the air receiving it without comment. Tension easing out of muscles that have been holding themselves up all day without you asking them to. Muscles in your shoulders, your jaw, your lower back, each one slowly letting go of a task it was never meant to carry this long. A rhythm in your chest, rising and falling, steady, the same shape over and over, the way a line traces evenly across a page when nothing is pushing it to bend. You do not have to solve for anything tonight. You do not have to isolate any unknown, or find what is hidden, or bring anything into balance on purpose. It is already happening, on its own, the way it always has, the way it will keep happening long after your thoughts have gone quiet and drifted somewhere else entirely. Your body knows how to balance itself. It has been doing it since the moment you were born, long before you had words for any of it, long before you knew what an equation was or what it meant to solve for something. 4,000 years ago, someone pressed a reed into wet clay beside a river, trying to divide something fairly, trying to find what was missing. A field needed to be measured, an inheritance needed to be split among children, a debt needed to be calculated in silver. That person did not know they were beginning something that would stretch across all the centuries to come. They were just trying to solve a problem, to find an unknown quantity, to make something balance that was not balancing yet. They pressed the reed into the clay, made their marks, and set the tablet aside to dry, and probably did not think about it again. Tonight, something is still being divided fairly, something is still being found, something is still settling gently into place, somewhere inside you, without any effort on your part at all. The same method that scribe used beside the Euphrates is being used right now, in this room, by your own body, balancing chemicals, adjusting temperature, evening out the rhythm of your breath. The scale is the same, the idea is the same, only the details have changed. If you were to hold all of tonight in one single image, as you drift now toward the edge of sleep, it would be this: a scale, old and simple, hanging perfectly level, one pan holding something known, the other holding something hidden, wrapped in a plain cloth bag, and a patient hand reaching in again and again, removing the exact same small amount from both sides at once, never disturbing the balance, only simplifying it, step by careful step, until finally, quietly, the cloth bag sits alone on its pan, and its weight is known. That is what algebra has been, this entire time, underneath every layer we added tonight. Not a set of rules to memorize, not a collection of symbols to decode, not a subject that belongs only to classrooms and textbooks and people with a certain kind of mind. It is a method, a quiet way of thinking, a way of treating something unknown as if it were known, giving it a temporary name and then working backward through fair moves until the unknown reveals itself. The Babylonians used it to divide land fairly along two ancient rivers. They did not call it algebra. They did not have a word for it at all, but they had the method, and they wrote it down in clay, and some of those tablets survived fires and floods and the rise and fall of empires, and they still exist tonight, in museums and library collections, marked with the calculations of people who lived 40 centuries ago and wanted to get the numbers right. Al-Khwarizmi gave it a name in a city built as a monument to learning, Baghdad in the 9th century, the House of Wisdom, where scholars from many cultures gathered and translated and argued and built on each other's work. He wrote a book that classified every type of quadratic equation and gave a guaranteed method for solving each one. He called the central operation Algebra, completion, the act of restoring balance by moving quantities from one side to the other. That word traveled through translations and centuries and languages until it became algebra. And his own name, al-Khwarizmi, traveled a different path and became algorithm, the word for any step-by-step procedure, any reliable method for solving a problem. He showed that one method could solve an entire family of problems at once, not just a single one. That was the leap, not finding the answer to one particular puzzle, but finding a way to solve every puzzle of that shape, forever, no matter what numbers appeared in it. The method generalizes completely. That is what makes it algebra and not just arithmetic. Descartes gave it a picture. Lying in bed, watching a fly crawl across his ceiling, he realized that two numbers could pin down any point on a flat surface, and that an equation with two unknowns could be drawn as a curve, a shape, something visible to the eye. Algebra and geometry, which had grown up separately for thousands of years, were suddenly revealed to be two views of the exact same truth. An equation was a shape was an equation. Solving an equation meant finding where a curve crossed a line, and two equations together meant finding where two curves crossed each other. Mathematicians gave it letters for the unknown and the known both, so that a single written line could describe every possible version of a problem, rather than just one specific instance. Viet used vowels for unknowns and consonants for knowns. Descartes refined it further, settling on the convention we still use tonight: X, Y, and Z for the things you do not know, A, B, and C for the things you do. The notation became stable, shared, a language that could travel across countries and centuries without losing its meaning. They extended it to handle negative numbers, which once seemed like nonsense, a fantasy, an impossibility. How can you have less than nothing? But mathematicians in India understood that negative numbers were not nonsense at all. They represented debt, or direction, or a deficit, something perfectly sensible once you stopped insisting that every number had to be a pile of physical objects you could hold in your hand. And once negative numbers were accepted, algebra became truly general, truly universal, applying the same rules everywhere without needing special cases. They extended it to numbers that seemed even stranger, imaginary numbers, the square roots of negative quantities. These began as a kind of mathematical fiction, a number nobody could quite believe in, given a name that was originally almost an insult. But they turned out to be essential, showing up in the equations that describe alternating current in your home wiring, in the quantum mechanics that governs the behavior of subatomic particles, in the signal processing that cleans up audio recordings. Something that began as a curiosity became indispensable. They extended it, eventually, to patterns so abstract they no longer describe numbers at all, only the pure shape of how symmetry and structure behave. Groups, the symmetries of a square, the shuffles of a deck of cards, the symmetries of a snowflake, all following the same small set of rules. And those patterns, studied purely out of curiosity, with no application in mind, turned out decades later to describe the deepest workings of physical reality itself. And through every single one of those layers, every century, every civilization, every notation change, the core idea never once changed. Something is hidden, something else is known, and there exists a patient, careful, repeatable way of moving from one to the other, a set of fair moves that never disturbs the balance, only clarifies it, until what was hidden finally, quietly, reveals itself. You have been doing a version of this your entire life, long before you ever saw a letter used to stand in for a number. Every time you noticed that something did not add up, and worked backward, carefully, to figure out what was missing, you were practicing algebra, in its oldest and truest sense. Every time you adjusted a recipe for a different number of people, every time you figured out how much time you needed to leave to arrive somewhere by a certain hour, every time you balanced your spending against your income, or divided a bill fairly among friends, or estimated how much paint you would need to cover a wall, you were solving for an unknown, using what you knew to find what you did not, long before anyone gave it that name in a city beside two rivers, a very long time ago. Algebra is not foreign to you. It is not something that lives only in textbooks and classrooms, accessible only to a certain kind of mind. It is a formal version of something you already do, naturally, without thinking about it. The textbook version adds symbols and systematic methods and general formulas, but the underlying instinct, the sense that something is missing and can be found by careful, balanced reasoning, is already there, already part of how you move through the world. The scale is the right image for this, the truest image. Not a machine, not a computer, not anything complicated or modern, just a simple balance, two pans, a central point, and the quiet understanding that whatever you do to one side, you must do to the other. That is the whole ethic of algebra: fairness, balance, patience, the refusal to force an answer by breaking the rules, the willingness to wait, to work step by careful step, until the unknown reveals itself on its own terms, not forced, not guessed, but found. And that same ethic, that same patience, is what your body is practicing right now, as you lie there in the dark. Your brain is balancing chemicals, adjusting the mixture, shifting the scale slightly towards sleep, then back, then towards sleep again, until eventually it will tip all the way, and you will drift off without even noticing the moment it happened. You do not have to solve for anything tonight. You do not have to isolate any unknown or bring anything into balance on purpose. It is already happening on its own the way it always has. Somewhere above you, whether you can see it through a window or not, the sky is still running on algebra. The planets are following their elliptical paths, each one tracing out a curve that Kepler described and Newton explained, and generations of astronomers have refined. The tides are rising and falling against every shore on Earth, pulled by the moon, following a pattern that can be written as a sum of waves, each wave a simple algebraic expression. The stars are burning, fusing hydrogen into helium, and the rate of that fusion follows equations that nuclear physicists have worked out over decades. The universe itself, in every direction, at every scale, from the smallest particle to the largest galaxy, is following rules that can be written in algebraic form. And yet none of that needs your attention tonight. The stars do not need you to watch them. The tides do not need you to calculate them. The planets do not need you to understand their orbits. They will continue, whether you are paying attention or not, whether you are awake or asleep, whether you remember any of this or let it all drift away. The same is true of your own body. Your heart will keep beating, your lungs will keep breathing. The chemicals in your brain will keep finding their balance, adjusting the mixture second by second, the same way that ancient scribe adjusted the scale, removing equal amounts from both sides, until everything settles perfectly level. You do not have to supervise any of it. You do not have to check the calculations or verify the results. It is all happening, quietly, competently, the way it was designed to happen, the way it has always happened. 4,000 years ago, someone pressed a reed into wet clay beside a river, trying to divide something fairly, trying to find what was missing. That person is long gone. The river has shifted its course. The city they lived in is a mound of ruins, excavated by archaeologists, mapped and measured and studied. But the idea they were using, the method of balancing an unknown against a known, is still here, still working, still finding what is missing, in devices and bodies and buildings and stars. Tonight something is still being divided fairly, something is still being found, something is still settling gently into place, somewhere inside you, without any effort on your part at all. The scale is level. It has been level for a while now. You can let go of it completely. You can let the balance take care of itself. You can let the equations solve themselves, as they have been doing all along, quietly, without any help from you. You can let your breathing slow, and your muscles soften, and your thoughts drift apart like clouds that have nowhere in particular to be. 4,000 years of algebra, and it all comes down to this: a scale, level and still, an unknown, finally known, a body, settling into rest. A mind letting go of its questions one by one until nothing is left to solve for, and everything is balanced, and the night is quiet, and you are asleep.